T-minus 1 minute. T-minus 30 seconds. We are go for launch. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Good morning and welcome to NASA's Lunabotics 2025 Finals event. We're broadcasting live from this amazing Center for Space Exploration, which is inside NASA's Kennedy Space Center Visitor Complex here on Florida's East Coast. My name's Kurt Lloyd. I'm a NASA software developer and robotics engineer. And I'm happy to be your MC, your narrator, and your color commentator, and anything else I can do. I want to give a big shout out to all the teams and all the staff and all the guests that are actually here in person at NASA. Let me hear you, people. We are also super excited for all of you who are watching this broadcast online from all over the world. Thank you so much for your interest in NASA and for your interest in this event. Please don't be shy about sharing our live stream link with everybody you know. Now, I'm not nervous at all. Ignore the shaking paper. Now, for everyone out there who's not familiar with NASA's Lunabotics event, allow me to quickly summarize. Lunabotics gives college and university student teams the task of designing and building working prototype lunar construction robots. During the robotic competition runs that you're going to witness later today, these robots are going to traverse complex and rugged terrain, and they'll dig and transport fine particulate material or simulated moon dust from one location to another location. It is an exciting competition, and I'll be here the whole time to help explain what's going on to the best of my abilities. We did have 35 teams compete last week in the Lunabotics qualifying event at the University of Central Florida in Orlando. And the top 10 teams from that event are right here, right now. These 10 teams that you can see behind me, and actually a lot of them are over there, these 10 teams are about to compete for the grand prize in NASA Lunabotics 2025 Finals event. Now, here's what we have on the schedule for today. And I'm going to need my cheaters. So, the opening ceremony will happen at the bottom of the hour, 8:30 a.m. For those that are seated there right now, it's good. You've got a good seat, but it will start at 8:30. I can't guarantee we have enough chairs for everybody. Matter of fact, I can pretty much guarantee that some of you will be standing. So it is a good idea to get here early, like I see a lot of the crowd has started. Most of these teams have come in early today, and they've set up in their pits, and they've started getting their robots ready for their competition runs later today. And those robot preparations, safety inspections, comm inspections are going to be happening all morning back here behind me. And then at 10 a.m., and for those online, I'm talking Eastern time, 10 a.m., we're going to have a demonstration in the Artemis Arena, and we'll talk more about that live when it actually happens. So 10 a.m., we're going to have a demonstration while teams are continuing to get ready for their runs. Our very first run of the day is going to start at 11 a.m. Eastern, and then we will have a break for lunch at 12, and then every hour from 1 p.m. all the way till 5 p.m. we will have runs. Actually, to be really clear to the teams that are here, the actual start of the run, the 30-minute timer in the arena, is scheduled to happen on the half-hour mark. So the the pit boss is going to tell you, when to, go into the arena and that sort of thing. This schedule that I'm kind of looking at is a guideline, and if we get ahead of schedule, that's okay. If we get a little behind schedule, that's okay. But the pit boss, which all the teams I'm sure have met by now and are familiar with, is going to be basically guiding our schedule today and making sure that we get teams running basically every hour. We do have some seminars happening today. We have a room behind you all who are sitting facing the stage. Behind you, across the hall, we have a seminar room set up, and hopefully you all have a copy of the schedule. At 11 a.m., we're going to have Blue Origin and Honeybee Robotics giving a presentation. Then at 11:30, we're going to have a presentation about internships. And then at 1 p.m., the Australian rover team are going to be giving a presentation. And I'll go over these again later, and hopefully we'll put them on the screen occasionally so you can all make note if you don't already have a copy of this schedule. 2:30 p.m. systems engineering presentation, and 3:45, I'm not sure, is going to be the Australian Rover Challenge overview. So that is a quick preview of our schedule today. And again, at the bottom of the hour, 8:30 Eastern, is when we are going to start our official opening ceremony for NASA Lunabotics 2025 finals event right here on the stage. So you have about 15 minutes, teams, to get a little bit more work done on your robot, get a little bit of coffee in your system, and then be here at the bottom of the hour for the big opening ceremony. You don't want to miss it. We will also be streaming that live. So welcome to those online, as I said before, and let's take a look at some live views around the building as we get ready for our opening ceremony here in just about 15 minutes or so. See you soon.
Did you know there's been over 1 million registrations in NASA's virtual guest program since May 2020? From your neighbor to the Crew 5 astronauts, you might be surprised who is a NASA virtual guest.
Do you have Mars 2020?
I do. Do you have James Webb?
Sure do. Do you have Crew 5?
Well, I've got it here, and you guys have it here, but I missed it here.
We conducted over 200 science experiments and technology demonstrations on our mission. We loved being part of Expedition 68. We even remembered a virtual guest passport for Einstein, our freefall indicator, but we forgot to register and missed the stamp.
Even if you're doing existing research, never miss a stamp from NASA's virtual guest program. Whether you're en route to the International Space Station or located anywhere around the globe, register at nasa.gov/virtual guests to receive updates on missions and milestones. As a virtual guest, you will receive curated resources and a stamp for your passport following a successful launch.
Remember, you only get the updates and stamp if you register.
I joined. I won't miss it next time.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
Go. Drop. Go. CD8. Go. Fido. Go. All right. Go for launch.
Our destiny is always to go and see what's further and what's next.
Fido. I'm running the flight.
Good morning, Lunabotics teams. And good morning, guests watching online. My name is Kurt Leutz. I'm a NASA software developer and a robotics researcher, and it is my distinct pleasure to welcome you to the Lunabotics 2025 finals here at NASA's Kennedy Space Center. All of you students have worked hard throughout the entire academic year to get here with your robots today, and you should feel pretty darn proud of that accomplishment. Now, for anybody in the audience who may not be completely familiar with Lunabotics, allow me to take just a quick minute to introduce you to the competition. Lunabotics gives college and university student teams the opportunity to learn and use the NASA systems engineering process excuse me, to design and build working prototype lunar construction robots. During the time competition, these robots must traverse complex and rugged terrain, and they must dig and transport fine particulate materials from one location to another. 35 teams competed last week in the Lunabotics qualifying event at the University of Central Florida in Orlando. And the top 10 teams are here at the Kennedy Space Center Visitor Complex. These 10 finalist teams will compete today and tomorrow and Thursday for the grand prize. Now, young Miss Dylan Dotson, please join me on stage. Miss Dylan is only 8 years old. There she is. Come on up here. She's only 8 years old. Hello. She's only 8 years old, and she is already a talented and experienced singer. She has agreed to sing the national anthem for us this morning to kick off our Lunabotics Finals event. So please give her a big hand of encouragement, and please stand for our national anthem. You want to hold it, or you want me to hold it? All right, go for it.
Oh, say, can you see by the dawn's early light what so proudly we hail at the twilight's last gleaming, whose broad stripes and bright stars through the perilous fight o'er the ramparts we watched were so gallantly streaming, and the rocket's red glare, the bombs bursting in air, gave proof through the night that our flag was still there. Oh, say does that star-spangled banner yet wave o'er the land of the free and the home of the brave.
Great job. Thank you, young Miss Dylan. That was amazing. I owe her mother an apology for standing right in front of her that whole time. Our next speaker comes all the way from our nation's capital. You may or may not know that Lunabotics is a product of and is supported by NASA's Office of STEM Engagement, or OSTEM. That's a group at NASA that focuses on inspiring our nation's students and educators about NASA's mission and encourages and helps build a STEM workforce that's ready to tackle NASA's future missions and needs. We are extremely happy to have the head of NASA's OSTEM, Miss Elaine Ho, here with us to help kick off our Lunabotics Finals event. Her resume is impressive. She received her bachelor's degree in civil and environmental engineering from Duke University. And she also received her Doctor of Law degree from the University of Florida. You may have heard of both of those institutions. Please help me welcome the head of NASA's OSTEM to the stage, Miss Elaine Ho.
Well, good morning, everybody. It's great to be here You know, when I think about exploring the moon or exploring the lunar surface, you got to think about NASA. And so that's why I am thrilled to be here representing NASA with all of my NASA colleagues to say congratulations to being one of the finalists in our 2025 Lunabotics Challenge. Let's just take a moment to applaud you all. So I heard that the theme for this challenge was good for NASA, good for America, good for all of us. And I think that that theme is spot on, because when I think about from your perspective how you got here, you might have done it as part of a senior design course or maybe part of a club or something fun to do with your friends, which I hope that was all the above. But I want you to know for NASA, it was something bigger, because what we're seeing from where we sit is that the aerospace industry is growing exponentially. And what that means for our needs, that means we need more people for more jobs. And that's where you all, as students who are ready to jump in, where you guys come into play. Now, you might be thinking a job with NASA or a job with one of our industry partners may be a ways away or you're not ready for it. But I want to tell you that everything that you have done to get ready for this competition today, you got a chance to feel like what it's like to work at a real aerospace job. So as Kurt described, yes, it's all about the technical design and the math and the physics and the engineering classes that you took and applying concepts to hands-on opportunities here, all of that. But there's some things that a classroom can't teach. Things like how to work in a team with team members that you might not have chosen. Like working out a problem when you've got someone with a very different perspective or background. Or overcoming and bouncing back from failure, which I'm going to guess that you guys encountered time to time in building your robots. And so I want you to know that those are the exact same skills that NASA and our company partners look to hire, no matter if it's a flight director or software engineer or payload operator. So I want everyone here to know that no matter who the winner is, no matter who gets what award over the next couple days, that each one of you have the amazing potential to have an awesome job and even awesome career contributing to America's space mission. So keep up the good work, because we're going to need you in the years to come. I want to take a few seconds to really acknowledge a lot of other people that made this happen. To all of our industry partners who really put in not just dollars, but their time. To my NASA colleagues who have volunteered and come from across the country to be here. To my Office of STEM Engagement team, and so many others. Because of your commitment, because of your dedication, these students have the opportunity to design and build and test hardware, skills that we know that we're going to need in the aerospace industry across the way. So thank you so much for your commitment, time, blood, sweat, and tears to make today happen. And they're going to ask me to get off the stage, so I'll just quickly say that, NASA today is all about getting back to the moon and then beyond to Mars, and that is a mission that we are really focused on. But we also have the responsibility of preparing our future leaders that will take us there. And that's who I see here today, our future astronauts and scientists and engineers and problem solvers. So cannot wait to see what you're going to do in the next couple of days, but really can't wait to see what you're going to do in the years to come. So good luck, and thanks, everybody.
Thank you, Elaine Ho. Very inspiring. Our next distinguished speaker comes all the way from, well, he came across that fence over there at KSC. He was born in Maryland, but as an Army brat, he grew up in Maryland, Texas, New Jersey, Indiana, Illinois, and even Hawaii. He received his bachelor's degree from the Air Force Academy and his master's degree from the University of Central Florida. He spent 6 years in the Air Force working space operations in Florida and in Colorado. Then he worked as an engineer for 5 years in the aerospace industry, first at General Electric Aerospace Group, then at McDonnell Douglas Space Systems Group. And then 11 years into his professional career, he finally came to NASA. He's been here for more than 3 decades, first as an operations engineer, and then helping upper management run and manage the entire Kennedy Space Center. Please help me welcome to the stage former Kennedy Space Center Deputy Director and currently the Acting Director of KSC, Mr. Kelvin Manning.
Thanks, Kurt. Good morning. I tell you, I do have one of the most exciting jobs on the planet, okay? But out of all the things I do here at the Kennedy Space Center, coming here this morning to welcome the Lunabotics Challenge competitors is one of the most exciting things I get to do. So welcome. Welcome to the Kennedy Space Center, the world's premier spaceport, as well as our world-class visitors complex. So hopefully you have time to take advantage to see everything while you're here, because it is truly fabulous, magnificent, however you want to describe it. So I look back on my computer. The first time I did a welcome here, we didn't call it Lunabotics. I see Rob here. We called it the Robotic Mining Competition. We started at UCF. I did that in 2014, so that's 11 years ago, doing a welcome to a group just like you. You guys were probably in elementary school back then. So what's the biggest difference? Well, the biggest difference is now we are closer to getting to the moon. Our Artemis 2 and 3 missions. Artemis 2 will launch early next year, sending a crew of 4 astronauts to orbit the moon. And that will be followed by our Artemis 3 mission, which we will land humans on the moon again, more than 50 years. But we're going to the moon now. NASA has a program called CLIPS. You know, we have a lot of acronyms: Commercial Lunar Payload Services. Companies like Astrobotic, Intuitive Machines, Firefly, who've already tried and landed payloads on the moon. And you guys, this team, you represent the future. Back in 2014 when I talked, we probably had maybe 12 launches here at the Kennedy Space Center. Last year, we had 93. This year, we've had over 42, and there's currently another 90 on the manifest here launching from the Florida Space Coast. So like Elaine mentioned, the future is bright, and there's a place for everyone here. You guys, if you don't win, so what? This is one of those experiences in life where you can look back and remember the time you came to the Kennedy Space Center, and it should be a pivotal moment to help you guide your path to the future. If it's a STEM field or whatever you do, take this experience and make the most of it. So again, welcome. And remember, we're just getting started, so I'm glad you're here. Thank you.
Thank you, Kelvin Manning. Always great to hear about the amazing work being done here at Casey, and thank you for encouraging the teams. Now, our next speaker was not able to be here in person, but please try to not be offended. I think in this case, she has a pretty darn good excuse. Please direct your attention to the screen.
Greetings from the International Space Station. I'm NASA astronaut Nicole Ayers. Orbiting 260 miles above our planet, we see firsthand how innovation, teamwork, and a love for STEM push the boundaries of exploration. What you're doing right now at the Lunabotics Finals at Kennedy Space Center, designing, building, and problem solving, is in the same spirit that drives NASA's missions. Whether it's to low Earth orbit, where we are, or to the moon, Mars, and beyond. One day, the technologies you're developing could help future astronauts mine lunar resources, build habitats, or even pave the way for deep space exploration. So keep experimenting, keep refining, and keep pushing the limits of what's possible. We can't wait to see what you create. Maybe we'll even use your ideas up here someday. Keep up the amazing work and enjoy the competition.
Well, how about that? It's not every day you get a pep talk from an actual orbiting NASA astronaut. Okay, there's only one person in this room who I think is appropriate to follow a pep talk from an astronaut who's orbiting the Earth. He needs no introduction to this audience, but I'm going to introduce him anyway. He's a mechanical engineer from the University of Miami, and he holds 2 master's degrees, one from the Technical University of Delft in the Netherlands, and one from Florida Institute of Technology. He's a NASA senior technologist with 11 U.S. patents under his belt, so far anyways. He's an expert in regolith, geotechnics, robotics, in situ resource utilization, planetary mining and construction, surface and ground operations, and much, much more. He is the co-founder of NASA's SwampWorks ISRU Research and Technology Group here at NASA's Kennedy Space Center. He basically invented this Lunabotics collegiate competition, and he brought it to life 15 years ago. In addition, he is our chief Lunabotics judge, and you all probably know that he is the biggest fan of all of you, the competing Lunabotics students. Please welcome to the stage, Mr. Rob Mueller.
Good morning. Thank you. So I want to correct Kurt. It wasn't just me that started this. Gloria Vigilante's here, and she was I like to call it co-conspirator, because we did conspire, and we managed to make this happen, and I'm very proud of all of you and the competition. I'll keep it really short because we have a lot of work to do today. But I just want to congratulate the top 10 for being here. And so a round of applause for the top 10, please. So as you know, we have a qualification competition at UCF because we just have too many teams. So we have a qualification round at the University of Central Florida, which you've all been to. And then the mission is to come to Kennedy Space Center and drive a robot on a simulated lunar surface, which we have. It's BP-1, Black Point 1 regolith simulant. It comes from a place near Flagstaff, Arizona, with a volcanic lava flow that's very similar to what you would find on the moon. First thing you're going to find, this is a different simulant than what you had at UCF. So you're going to find it's very abrasive, sharper. It might behave a little bit differently than the Lunar Highlands simulant. You're going to find that out when you drive your robot. But it's definitely different than sand, right? Regolith simulant is different than sand. And that's one of the big takeaways you should have from this competition, is you have to learn how to deal with the lunar environment. So I also want to congratulate all the other teams that didn't make the top 10. Just raise your hand if you're here, but you didn't make the top 10. Okay, see? Still hanging in there. And guess what? They all have to work, and you get to go see the visitor center. So it's not all bad. But I think it's still a good experience. That's the main thing. There's only 3 things you need to do during this competition. You need to be safe, you need to have fun, and you need to do good work. And if you take those rules and apply them to life, I think you'll be fine. So let's just get into it. I have a list of the top 10 here, and I'd like you to show your spirit, please, any way you would like. Keep your clothes on. Number 10, Milwaukee School of Engineering. Michigan Technological University. Nice. University of Virginia. University of Utah. Okay, that's the most spirit so far. Colorado School of Mines. Okay. University of Alabama. I knew that was coming. College of DuPage. Excellent. Purdue University. Boiler up, hammer down. I like it. University of Akron. Wow, in stereo. And finally, the University of Illinois in Chicago. Nice. All right. I can see you've had your coffee. Now get to work. Thank you.
Thank you, Rob. See, I told you he was your biggest fan. Now take that energy and that excitement and focus it into the next 3 days of competition. But please don't let this week go by without stopping to enjoy it. So take a deep breath. Everybody take a deep breath. And don't panic. And speaking of not panicking, please use written checklists or similar tools to make sure you don't forget to turn on or remove something that's important enough that it ruins your competition run. You've come too far to let a silly mistake or a simple oversight wreck your team's chances of success. So be careful and be thorough. Competition runs are scheduled to start at noon today. Make sure you take your robots through the required pre-competition inspections as soon as you and your robots are ready. We will be broadcasting starting at 8 a.m. Eastern every day, Tuesday, Wednesday, and Thursday on NASA Kennedy's YouTube channel from our broadcast desk right here in this room. So tell your friends and family so they can follow along and watch live. There is a very simple link where you can find Lunabotics, including our live stream. It's go.nasa.gov/Lunabotics. That's go.nasa.gov/Lunabotics. That will take you to the Lunabotics homepage, and there's a link to our live stream right at the top. Now let's all go back to our pits, and let's put all those finishing touches on our lunar regolith construction robots. Good luck, teams, and don't forget to have fun. Oh, and one last thing. Robot drivers, start your robots!
So for the Lunabotics staff, Lunabotics judges, please meet in the arena room. We have a team photo to do. So that's, once again, all the staff, all the judges, anybody that's helping to make this thing happen, please meet in the arena room for a team photo.
The space station is a great platform to test not only the hardware but the operations of living and working in space. The beauty of the space station is that if something goes wrong, we can get ourselves safely back to Earth in pretty short order. We don't have that luxury when we go to deep space, so this is the place where we make sure we've got it all right before we send our friends and colleagues out into deep space. I think the most important thing we've learned while living and working on the space station is that we can only do it when we're all on the same page. We work with different people, different cultures, different nations, and it is amazing to see what we can accomplish when that machine is firing on all cylinders. And we do it every day, and we've been doing it for decades. Nobody does this alone. Human spaceflight is a team sport, and without the hundreds of thousands of people who are supporting it, we would never be able to do it.
The ISS is the most incredible wonder of the modern world. NASA's learned a lot of things from the ISS program, both fundamental biological and physical sciences, but also exploration. The single greatest achievement that I feel that the ISS program has produced is that we can grow crops normally off Earth. My favorite memory of ISS support is Scott Kelly did a bouquet from the zinnias. He created the first ever off-Earth flower arrangement. What I hope to see from the ISS as we move forward is more tests of sustainable technologies and approaches like crop production.
We've laid a foundation and an experience base across NASA and across the globe that's going to serve us very well as we move into exploration, both in low Earth orbit as we continue, but also for Moon and to Mars. Human spaceflight is really complicated and it's really unforgiving. Assembling space station was really complicated, yet we successfully did that in space, on orbit, and created the most advanced and complex spacecraft that's ever been built. We have spurred a commercial interest. We've spurred a government interest. There's a passion for space that didn't exist before. I think that inspiration, that motivation that we generated across the globe is probably the single most astounding accomplishment that we've had with the space station.
From the ISS program, NASA's learned really what happens to the human body in zero-G over long-duration flights. When we go to Mars, we'll be committing those people to a long-duration mission, so it's imperative that we know what that's going to do to their bodies. You know, I think the greatest thing the ISS has taught us is really that you need to be flexible and modular. We've moved modules around on the ISS, we've moved docking ports around. I wish everybody understood that the ISS requires a large team of people that are looking at millions of pieces of data every day. It's a very detail-oriented operation. So my best memory of ISS support is actually a personal memory. I met my wife there. We were both flight controllers. We met in MCC, and actually I proposed to her in the flight control room. As the ISS moves forward, I hope to see it continue as a zero-G laboratory. I hope to see it as a test bed for long-duration deep space missions so we can test out new hardware and designs.
My best memories are the stressful ones, but when we've had things that have gone wrong on space station that needed to be fixed quickly, just watching the teams, the leaders, the engineers, the safety folks, the health and performance folks all come together very quickly, sacrifice time with their families, work 24 hours a day until that problem was fixed and solved. It's just amazing watching the people come together to keep this thing working. NASA has learned so much from the ISS program. It's amazing. Everything from how to live in space for long periods of time. And for me, from the engineering side, what we've really learned is how do you keep a really, really complex machine working continuously? Those are questions that we need to answer to make it to Mars, to far-off destinations, and the space station has been really important for helping us get there.
NASA has learned so much from the ISS program. That collaboration across different countries with a common goal has been significant. Since we started building this project here at the Kennedy Space Center, we had to assemble all the components and test the systems to make sure that they will work here as they were intended. When I originally started, ISS was only supposed to be 15 years. Now we're at 25 years. So being able to see that still in space, and now I'm launching astronauts that are going to ISS to be living in those modules that I help test and integrate here on the ground is extremely rewarding. As ISS continues its mission, I hope that we see a lot of more breakthroughs in research. So I hope that all the different testing is going to enable us when we go to the moon and to Mars to better understand how the human body will endure during those long duration missions.
In terms of the next decade of space station operations, I really think we can continue to take advantage of the tremendous laboratory. We continue to learn more about material science, human research, help position ourselves for exploration. I think space station's an excellent test bed for exploration. We've done numerous things on space station to test exploration ops. It's a series of habitats that you have to keep sustained, and then you have to integrate those science operations for multiple crews, and so it's a good surrogate for a lunar base or even a Mars base someday. It's just an incredible facility, and the fact that we've had between 2 and 6 astronauts in orbit continuously for 23 years and how challenging that is. We have an incredibly dedicated, talented team, and they are there to make the flight successful and make them safe, and I see that every day, and I'm just proud to be a part of the team.
Christina Cook of NASA, the first one through the hatch, being greeted by her crewmates aboard the International Space Station.
The one thing I wish everyone knew about the space station was really that we've had astronauts off the planet for 23 years continuously. That to me is just incredible. The greatest single thing that we've learned on the space station is to grow and eat our food. When we're on Mars and we're growing and eating our food on Mars, we're going to trace that all the way back to the space station. Well, the astronauts grew and ate the red romaine lettuce on space station. It was Scott Kelly, Kjell Lindgren, and Kimia Yui. Kjell harvested the lettuce, and then they shared the lettuce, and they did a cheers. They toasted the lettuce and ate it. Another really great memory of space station was when Scott Kelly unbuckled the zinnia flower that he grew. It was really fun to see him take it out to the cupola. I hope to see continuously produced crops on space station for deep space exploration missions.
I think
Folks don't realize that it takes an army of folks and a huge effort to safely operate the ISS and make sure that we can continue to do the work that we do and to provide those science and research activities. I think that NASA has made something very hard look very, very easy. I don't think the general public realizes the behind the scenes that goes into making that such a success and really giving all those teams of people, you know, the accolades that they deserve. We've learned so much about international cooperation. I mean, the ISS has been successful because of the international partnerships we've had. We've learned the importance of that both in developing technologies, collaborating on science, but also in terms of foreign policy and national interest.
NASA's learned a tremendous amount from the International Space Station, not only from a technological perspective, but from a human side as well. The ISS is a marvelous technological platform for science. But what we have learned as an international community, crossing cultural differences, political differences, to support the men and women who are willing to go into space for exploration and science on behalf of all humankind, I think is one of the legacies that we're going to have. When you go outside at sunset or early in the morning and you track the ISS coming over your locale, realizing there are human heartbeats on board going at 5 miles per second. It's very special to realize that they are our friends, their families are important to us, and we do everything we can to maintain all the best of their health and well-being.
I get to help the astronauts launch and return from the International Space Station. There's been a lot of learning happening over the last couple years, 25 years now. I wish that everyone would know that the space station is one of the biggest international collaborations that NASA has. I think it is the foundation and testbed of just humanity's effort in space. The first ever flown in space object I got to touch was from working on ISS. Advanced Plant Habitat did an amazing thing where they flew some patches for us on station and returned them for the team that worked on the Advanced Plant Habitat project. So as someone who grew up loving space and wanting to work at NASA for more or less my entire life, that was a pretty impressive memory and remains something that I hold very dear. Moving forward, I hope to see more experiments, more of the science that gives us perspective on the human body and the workings in a zero-gravity environment, which will allow us to understand a microgravity environment like the moon or on Mars.
It's the only place in the world that we can do microgravity research. Think about that. One place in the whole world. There are no chambers on Earth where we can replicate microgravity, just the space station. So we have to use that in order to figure out what we need to do for exploration. The first thing we learned is what we didn't know, right? The questions we needed to ask. Moving from shuttle to space station, going from short duration to long duration, we discovered many, many things that we didn't even know were risks of spaceflight. But we can use a space station as a space analog for other space destinations. So that's really where we're going to focus, is how do we get to the moon safely? How do we get to Mars safely? Space station will allow us to do that.
International partnering, international cooperation, engaging research, those three things to me are one of the most important things that the ISS has provided. You know, when we embarked in processing the elements of the ISS, nobody knew how to do it. We kind of figured that out as we were going through it. One thing that everyone should know about the ISS is that it's a great platform to do research, and that we need that platform and future platforms to help us understand how we're ever going to be able to go even farther out into deep space.
You know, in terms of what I want to see, I think the continued amazing science that the ISS provides, a little a little bit of what they have provided to humanity is going to pay big dividends down the road. The deep space explorers that go beyond low Earth orbit, they're going to take a lot of things from the ISS. The ability to do things autonomously by themselves without the ground helping them is going to be one of the key things that the ISS provides them. The one thing that I hope people realize about the International Space Station is that it is not just America's, that it's humanity's. We're not just doing things for the benefit of the United States. It's just bigger than what we are.
Every new day for us now is a record until you come home. Thanks for that.
The space station is a platform for bigger and more complicated exploration. The greatest achievement of the space station is collaboration. To work together, countries come together, and once we are on board of the space station, living there in the case of the astronauts, we are all the same. It belongs to humankind. It belongs to all the nations that have collaborated and built this station, and furthermore, it belongs to all humans because of what we are researching and discovering for a better life on Earth.
I wish everyone knew that the space station is just a technological marvel designed by engineers all over the world. I think the ISS has a lot to offer for deep space explorers. It's helping us learn how to design and operate systems to keep humans alive. One day that stands out to me is when we launched Crew 1. I was the mission manager for that mission, and it was just an incredible achievement to finally be providing crew transportation services to ISS, which is the whole reason that commercial crew program exists. I think the most important thing we've learned through the ISS program is the great things that we can achieve as really a human species if we work together.
Happy 25 years to the International Space Station.
Happy birthday, ISS.
Happy 25 years, International Space Station.
Happy 25th, ISS.
Happy 25 years, International Space Station.
Happy 25 years, International Space Station.
Happy 25 years to the International Space Station.
Happy 25th, ISS.
Happy 25 years, International Space Station.
Happy 25th birthday, International Space Station.
Happy 25th anniversary, ISS.
Happy 25th anniversary, ISS.
Happy 25 years, International Space Station.
Happy 25 years, International Space Station.
Happy 25 years, International Space Station.
We can't wait to see what's next for the space station.
NASA is preparing for a journey back to the moon, and after that, we're setting our sights on Mars. To get there, we need tons of rocket power coming from our Space Launch System.
When it comes to how much power this thing can push out, this thing is massive.
It's going to be mesmerizing to stand next to this massive vehicle. The immensity of it, knowing that this thing is going to be propelling a rocket into space and around the moon.
Hang on, it's probably best to start back at the beginning.
Vehicle, of course, it's produced all across the country. Components all come here. They may be built around the country, but they all come together right here in the Vehicle Assembly Building.
Our SLS rocket will generate 8.8 million pounds of thrust to break through Earth's gravitational pull. That's more power than the Space Shuttle and the Saturn V rocket used. Teams with NASA's Exploration Ground Systems are responsible for assembling the boosters that will house the majority of that power. The twin solid rocket boosters, made up of 10 total motor segments, will stand nearly 17 stories when fully stacked. First, teams will inspect and prep the hardware. Next, they're ready to start stacking the segments, a process that takes time, patience, and a steady hand.
Once we have everything done in High Bay 4, we pick up the segment with the 325 crane, pick it up over the 16th floor crossover to where you see it now, and we begin stacking the segments. Each segment, we lift over the 16th floor crossover and stack it. Once we stack it, we put it on top of the segment below, and we put about 177 pins all the way around the whole thing to attach each segment.
And the pressure to perform the operation flawlessly can test the team's nerves.
There's a tremendous responsibility involved with processing flight hardware like this. It's nerve-wracking at times, but it's exciting. There's zero appetite for risk in a program like this.
We have a bunch of shuttle guys that are here to show us along the way. You know, if we get stuck, they're there to guide us. At the beginning of the stacking, it was very nerve-wracking. You know, with each segment that we stacked, a little bit of the nerve comes off. By the third or fourth one, it's easy peasy. You know, we're pushing through, all the jitters are gone, and we're just excited to get finished with it.
With all 10 booster segments now fully stacked on the mobile launcher, there's just one final piece of the puzzle to round out the power needed to get SLS off the ground and send it to space. Core stage. After a 900-mile journey aboard NASA's Pegasus barge, the SLS core stage, the largest rocket stage NASA has ever built, has made it to Kennedy Space Center.
Today is a huge day. This is the last piece of big hardware that we need for Artemis 1 processing. And we've just been
that looked at systems individually before culminating in pure power. With over 700,000 gallons of propellant flowing through the core stage and its RS-25 engines firing for 8 minutes straight, the successful final test resulted in some big emotions from the team.
We cried, we laughed, and we cheered because it was so emotional to see, the years of culmination coming through.
And that victory did not come without overcoming a few challenges, proving why at NASA we test as frequently and as hard as we do.
And we got to shut down. All personnel.
So we actually did a 1-minute test on the first hot fire test. And then we learned a lot from that. We understood the vehicle more, we made a few changes, and then we got back into our second hot fire test.
There was a lot of joy and workmanship and ownership of being able to work that process and be able to get it done. When we went for the second hot fire, and we went for 500 seconds, that was just pure exhilaration.
Following its arrival at Kennedy, teams moved the core stage into the VAB, where it was lifted by a crane and placed in between the twin solid rocket boosters. Serving as the backbone of the rocket, the core stage will provide more than 2 million pounds of thrust to help send the Orion spacecraft on its trip around the moon.
Essentially, we have these two massive cranes that are located inside of the BAB, where we go ahead and we pick 2 points at the end of the core stage, one on the back portion of it and on the front portion of it. We lift it up to the point where we're able to transition it from a horizontal position over into a vertical position, and then essentially bring it way up to the top of the vehicle assembly building and cross it over into high bay 3, in which we ensure that we don't damage any part of the vehicle as it's incoming into its position.
NASA's largest rocket stage, now fully integrated with the twin boosters, is ready to get Orion off the Earth. But it will take one more critical component to give the capsule that extra push it needs to journey tens of thousands of miles beyond the moon. With just a single RL-10 engine, the Interim Cryogenic Propulsion Stage, or ICPS, will provide over 20,000 pounds of thrust to send Orion on the ride of a lifetime. To connect the ICPS with the rocket stack, teams next added the Launch Vehicle Stage Adapter to the core stage, followed by the ICPS.
The ICPS is the Interim Cryogenic Propulsion Stage, and essentially it's somewhat of the upper stage of the entire SLS vehicle. And what that will do is propel the Orion capsule along with its service module over to its destination, which at this point in time will be the moon.
But before the spacecraft can be attached to the rocket, teams will conduct a series of tests to ensure all of SLS's components communicate properly with one another, plus the ground systems equipment, the launch control systems, and its software. Adding to the challenge, those methods for testing have changed significantly since the days of the Apollo program. Initially built in the 1960s to house assembly of the Saturn V, the VAB has undergone some major modifications to support several different kinds of rockets and spacecraft, whether they're going into low Earth orbit or venturing to deep space.
This high bay was Shuttle Heritage. Before that, it was Apollo Heritage. So there's upgrades that are still occurring today to include upgrades that will support Artemis 2 and Artemis 3.
Wet
What an exciting day at the Kennedy Space Center. You can see the Orion spaceship coming out of the ONC building where we've been assembling it for several years. As big a step as this is for us today, rolling out and starting the journey of Artemis 1 to the moon and beyond, we're really excited for this test program to get this vehicle flowing and to begin the next steps, which are to send humans back to the moon.
The twin sister of Apollo, Artemis is the name given to the program that will return humanity to the moon. And named after one of the largest constellations in the sky, Orion is the spacecraft destined to get us there. Through Artemis missions, NASA will land the first woman and the first person of color on the lunar surface. And these missions will allow us to explore more of the moon than ever before, paving the way for long-term presence in lunar orbit.
We're rolling the Orion spacecraft out, but it's beginning its journey. We're really kind of at the end of the building process and the beginning of getting ready to go fly.
But before Orion can travel to our nearest celestial body, it must first make a few pit stops along the way to fuel up and get ready for flight.
As we leave here today, we're going to go to a facility that'll fuel the spacecraft with the rocket fuels and propellants it needs. We'll put a launch abort system on. We'll send it out to be stacked in the rocket and launched. And it's really the last few yards of the game.
Orion's journey to the moon began on the bayou. NASA's Michoud Assembly Facility in New Orleans is where technicians with Lockheed Martin began welding the pieces of the spacecraft's underlying aluminum structure together. 1 year later, it arrived in Florida, taking up semi-permanent residence inside the Neil Armstrong Operations and Checkout Building at NASA's Kennedy Space Center. Engineers and technicians will spend the next years working almost around the clock, outfitting Orion with thousands of components and pushing the capsule through several rounds of rigorous testing as teams prepare for its flight around the moon. The first step, though, is the crew module's arrival.
When the crew module shows up here at the ONC building, it's really just a welded shell of the structure. When it gets here, we put it into a fixture called the bird cage tool, and we use that fixture to position and attach all of the mechanically attached primary and secondary structure for the crew module.
Part of that includes the heat shield, which protects the crew module as it blazes through Earth's atmosphere at astonishing speed as it returns home. Technicians with Lockheed bond those thermal protection system products onto the heat shield right here in the ONC. And they do the same for the crew module's forward bay cover.
We bond that on here, and basically this covers the forward bay of the crew module such that once we come back into the atmosphere, this gets jettisoned and all of the landing system, i.e. parachutes, get deployed and slow the crew module down so that when it touches down in the ocean, it's only going a few miles an hour.
With the primary and secondary structures all attached, the crew module is tested to see how everything holds up. Orion is pressurized, stressing the welds to ensure they'll hold up under the proper loading. Afterwards, non-destructive evaluation of those welds is conducted to check for any voids or cracks. Once the structure is deemed strong enough, the crew module is moved just a few spaces down into the ONC's clean room for its next round of integrations.
We bring that structure into our clean room, which is you see behind me, because we need to start integrating the propulsion system and elements of the environmental control and life support subsystems, and those systems require a cleaner environment than the one we're standing in out here.
When all of that is done, the crew module is on the move again to the crew module integration station. There, all of the electrical systems, including wire harnesses and avionics boxes that control the crew module's guidance, navigation, communications, and its power subsystems, are integrated. Next, it's time to bring the spacecraft to life.
We power it up, And then we go into a whole series of functional tests to make sure all the subsystems that we've integrated up to that point are functioning properly.
But the crew module isn't the only thing that makes up the Orion spacecraft.
All the people, the work, the components that have gone into this vehicle, it's just an amazing feat.
Teams also worked closely with the European Space Agency to build the service module, the element that will power Orion on its journey around the moon. Once that arrives, from Bremen, Germany, Lockheed moves forward with integrating the two.
The service module has a very similar life cycle to the crew module. We build it up structurally, we integrate the propulsion system and the other fluid systems, and then we integrate it electrically and power it up and do functional tests on it. And when we have a full service module and a full crew module, then we stack the two together and we have what's called the crew service module for Artemis 1.
Under the Artemis program, NASA plans to not only return to the moon, but to use that as a stepping stone to go farther than any human has ever gone before, Mars. To get there, it's truly a cross-country and international effort among thousands of individuals.
When you consider all the people, at the Johnson Space Center, Marshall Space Flight Center, all across the agency, SLS, Orion, the European Service Module, Boeing and their team, Lockheed Martin and their team, and to see all of that come together on that launch when we send it on its way to the moon, it's going to be absolutely amazing, and we're going to have a lot of really proud, happy people.
Building a spacecraft destined for deep space exploration from the ground up is no easy task. And the fact that these teams have been able to come together and do just that in the midst of a global pandemic is nothing short of amazing.
It really is a testament to the workforce. If you think about what we've been through over the years that they've been putting this together, and particularly think about the environment that this team was dealing with. We're dealing with COVID, and we're asking these folks to come into work every day and finish the spacecraft so we can keep this mission going. And we're ready, and we're excited. And so as they turn this over to us, we're ready to get going.
And really, this is only the start of Orion's path to the pad.
It's a little hard to put into words when you think about the fact that we are in the first flow of what will be our nation's deep space exploration program. It hits you in the heart, and it really speaks to why we all are doing what we're doing.
I never thought as a little kid growing up I'd be part of something like this today. Now as a dad of two young girls, to be able to tell them what I do and to be able to have them someday watch the first woman stand on the moon is pretty amazing to me personally.
As the Orion spacecraft departs the ONC, its next stop is the Multi-Payload Processing Facility, or MPPF, where teams with NASA's Exploration Ground Systems and prime contractor Jacobs will perform the next set of milestones, fueling and servicing the spacecraft.
We have a few months of hard but rewarding work ahead of us to get to launch, but this is it. This is our year. This is our time and what folks have worked so hard for.
Now, we're going to continue with processing, get that thing checked out, fueled, get the launch abort motor stuck on top of it.
With fueling of Orion's crew and service modules complete, the spacecraft moves from the MPPF into the Launch Abort System facility.
We just finished fueling the spaceship, and we moved it to the LASA facility, the Launch Abort System facility, to put the Launch Abort System on the top of Orion.
And in July 2019, teams completed a critical test, the Ascent Abort 2 flight test, to validate the Launch Abort System works as expected. After reaching an altitude of about 6 miles, where the test spacecraft experienced high-stress conditions expected during launch, the abort sequence triggered. Within milliseconds, the abort motor fired to pull the crew module away to safety. Its attitude control motor flipped the capsule into the proper orientation, and the jettison motor fired to release the crew module for a splashdown in the Atlantic Ocean.
I feel, just honored and humbled every day to be able to work on this.
This rocket is just going to be absolutely amazing.
Now that the spacecraft's launch abort system is securely in place, Orion is ready for the next stop on its path to the pad, the Vehicle Assembly Building. Once inside, the spacecraft will be placed on top of the Space Launch System rocket, the most powerful rocket the world has ever seen.
You are watching NASA's 2025 Lunabotics Finals, which is just getting started here this morning here at the Kennedy Space Center Visitor Complex at NASA. And in the room here, we have 10 finalist teams who have made it through the qualification rounds last week in Orlando and are going to be competing today, tomorrow, and Thursday. Each team's going to get 2 runs, and we'll show you the details in a bit of where these teams are going to run. What's happening right now is the teams are getting briefed by various staff. They are going through inspection stations, which you're seeing on the upper right-hand side of the screen. And one of our teams in the room is actually from Australia. They're not officially competing in the finals this week. They are going to be demonstrating here at the top of the hour their robot, which won another event in Australia, a similar event in Australia. And so that's coming up at the top of the hour. Our Australian team appears to be on schedule. They've gone through their inspections, and they're basically getting suited up right now. On the left side of the screen, you can see students being suited up in white bunny suits, and those suits are going to keep those students from getting completely covered in simulated lunar dust while their robot is competing and kicking up dust. So stay with us, and things are about to get exciting, at least for a demonstration of a robot operating on our simulated lunar landscape here at the top of the hour. So don't go anywhere. This is NASA's 2025 Lunabotics Finals event here at the Kennedy Space Center Visitor Complex in sunny Central Florida. You're watching NASA's Lunabotics Finals event here at the Kennedy Space Center Visitor Complex in Florida. What you're seeing on the screen right now are our arena staff, our arena judges, all suited up in their protective equipment, and they are preparing the arena for the start of our demonstration event, which is going to be coming up here soon. The arena is filled with a simulated lunar soil that these robots are going to be digging in and then moving. The robots in this competition are all designed to dig in lunar soil and then construct berm structures or hills. And for NASA, berm structures are going to be useful on the moon in the future to protect sensitive systems like lunar habitats and propellant tank farms from rocket blasts during lunar landings and subsequent launches. Also in the future on the moon, piles of lunar soil are going to be useful as protective coverings that will insulate our sensitive systems from the sun or from destructive energetic particles and harmful radiation. The robots in this competition will be digging in that simulated lunar soil and then moving it to the spot that is shown on the screen right here that is between the 4 orange posts. And any of this simulated lunar dirt that they are able to collect and deposit in that in the middle of those 4 posts in our scoring zone is going to give them a good score in this competition. Our simulated lunar regolith that is in the bin is a volcanic rock that has been crushed to a fine powder, and it turns out that this actually makes a pretty decent stand-in for lunar soil. It ends up being light and fluffy on top, sort of like talcum powder, and underneath it becomes pretty hard-packed, underneath the top few inches at least. And it turns out that's exactly how lunar soil feels. And so you'll notice all of our judges who are in there working inside the arena that are working directly with this simulated lunar soil, they're wearing protective garments, and that entire arena is hermetically sealed. They also wear eye protection and masks due to the small particle sizes, which can become airborne, and also because the particles can become airborne and cause skin and eye irritation. What will become quickly apparent as you watch these competing robots here today is that lunar regolith, along with our simulant, is light and fluffy on top, as I mentioned, and hard-packed underneath. And that makes it fairly interesting for these robots to interact with. Your robot is going to sink down a few centimeters to get to that hard-packed surface. And most of the robots will drive around on that hard stuff underneath a few inches of soft stuff. Unless, if their driving actually loosens up the hard packed material that's down a few inches, they can make that light and fluffy too. And in that case, their robot may sink down and get trapped in deep fluffy material. And that's not the only thing that makes this competition a challenge for robots. The hard-packed material underneath is a lot harder than you think. The individual particles were created by energetic impacts on the moon, and so since the moon does not have an atmosphere and it does not have water to wear down and smooth out those particles, each particle is jagged in shape, and that's actually true for our lunar soil simulant too. And those jagged particles, when they settle together and they pack together under the weight of the material above it, they actually interlock and hold tight together like puzzle pieces, and that can become kind of difficult to penetrate. And so that makes digging in this material beyond just a few inches pretty difficult. this is part of the challenge that these students have to overcome in designing and building robots to drive on this material and to dig in this material and to move this material from point A to point B. Our Australian demonstration team has entered the arena. It's going to take them a few minutes to go through their safety checks and actually put their robot inside the bin. We can actually see the team on camera too, just outside the bin. They're all wearing bunny suits also. And they've got their robot on a cart and they're ready to bring it into the bin. In this view, you can see the corner of the arena has been marked off with a chalk line. And that corner of the arena is where all of our robots are going to start their mission. And we're basically simulating that the robot has been carefully placed there on the surface after it has landed on the moon. And each mission for these robots is going to be to start in the starting location, which is in the upper left hand of this shot. They're going to drive to the right in this shot into a zone of our arena that is filled with obstacles like rocks and craters. So they have to get through the obstacle zone. If you don't mind going back to that other shot, they have to go through the obstacle zone and then make it to the lower right quadrant in this image, which also has some rocks, but this is the quadrant where they are allowed, the only quadrant where they are allowed to dig or excavate material. Once they've excavated material, they need to get it to the lower left quadrant in this shot where the 4 orange markers are, and that is basically the scoring zone. Any material that is deposited into that scoring zone will give the team points based on the volume of the material that they have deposited in that spot. And we have high-tech laser scanners that will scan the surface before a team's run and after a team's run and calculate the difference between those two scans in order to calculate the volume of material that a team has deposited into that zone. So in just a few minutes, we are going to have the team from Australia give a demonstration run. Now this team are the winners of the Australian Rover Challenge. And that challenge is organized and run by the University of Adelaide in Australia. The team name is Queensland University of Technology. They're not competing for points here in the Lunabotics finals. They basically came here to give us a demonstration of their robot. So we're going to start our day with that. And it's going to be exciting to see a team from Australia show us what their robot can do and show us why their robot won the Australian Rover Challenge recently. So we should see that Australian team enter the arena as soon as the arena judges are ready and have performed all their pre-run checklists. You're watching a live feed from NASA's Lunabotics 2025 finals event. We are getting very close to the Australian Queensland University of Technology from Australia. That team is getting prepared to put the robot into the arena to perform a demonstration run, not for scoring, in order to show off their winning robot. And then what's going to happen after the Australian team runs is, well, for those in the room, at the top of the hour, we've got some presentations going on, Blue Origin and Honeybee Robotics at the top of the hour. Then at 11:30, a presentation about NASA internships. Our first team that is going to run official for scoring is going to be Michigan Tech. And if we are able to get Michigan Tech run before lunch break, our lunch break will include a quick award presentation. We will give out awards for STEM engagement, and we will give out the awards for presentations and demonstrations. After lunch, we will have the University of Virginia team run, and then the University of Alabama team, and then Milwaukee School of Engineering, and then University of Utah, and then Colorado School of Mines. Unless we run out of time before then, we should be able to get 6 scoring teams in today in this order. Of course, order could change. We are flexible, and if things get in the way, we are able to move teams around. But right now, as it stands, the plan is to do Michigan Tech, University of Virginia, University of Alabama, Milwaukee School of Engineering, University of Utah, and Colorado School of Mines. And for those students who are in the building and are not watching remotely, do not forget about the seminars. Keep your eye on those seminars. We've got Blue Origin and Honeybee starting out a seminar, then NASA internships. Those are both before lunch. Then after lunch, we've got the Australian Rover Challenge results presentation, and then a systems engineering presentation, and then a Queensland University of Technology journey at the Australian Rover Challenge presentation. That basically is what we plan to get through today. And again, for those teams that are in the building, don't miss out on these seminars. This is a great opportunity to see some great presentations on these very interesting topics. And soon we should see the Australian team putting the robot in the bin for their demonstration. All right, we're watching the Queensland University of Technology team in the control room. Earlier we saw the team putting the robot into our simulated regolith bin. While they were doing that, part of their teammates were taking all their computer equipment and networking equipment into the mission control room, which does not have any visibility into the arena other than 2 house-supplied cameras that teams are allowed to choose whether or not they want to view them. This Queensland University of Technology team has definitely chosen to use both of our house-provided cameras, because you can actually see the cameras on the 2 monitors in front of them that are being supplied by NASA Lunabotics competition. The students in the control room have 1 overhead camera, which is in the upper part of the screen, the right monitor in front of them. They also have access to a camera that is pan, tilt, zoom controllable by the students themselves, and that's shown on the monitor on the left side of the screen in front of the students. You can see that they have 3 students in the control room, 3 laptops that they brought with them. This is the setup time. Teams get 10 minutes worth of time to boot up their equipment, boot up the robots, plug in their networks, and make sure that they can wirelessly communicate with their robot and verify that it's ready to perform in the competition. During the 10-minute setup time, the control room students are allowed to use our house-supplied radio to talk to the students in the arena. This allows them to troubleshoot any issues that might happen, turn switches on and off, unplug and plug things in on the robot. But after the 10-minute setup time is over, the students in the control room will no longer be able to talk to the students in the arena. Matter of fact, the students in the arena will basically leave the arena, and the students here in the control room will be controlling the robots. I want to say blindly, but they won't have direct line of sight with the robot. They will only have data from the robot and a couple cameras that we provide them if they choose to use them. The reason these 2 house-supplied cameras are optional is the scoring for this competition isn't as simple as the team that makes the largest berm or hill wins. There are a lot of variables. The weight of the robot is part of the equation. The power used by the robot is part of the equation. The bandwidth, the amount of data that is passed between the robot and the students in the control center is another variable. So Queensland University of Technology, as I mentioned earlier, is just demonstrating the robot. They're not competing. But all the other teams you're going to see here this week are making all of these trade-offs in order to try and maximize their score in this competition. So 5 minutes left in the setup time for Queensland University of Technology. All right, the 30-minute timer has started, and this team, you can see controlling their robot using their joystick. Each team is going to get 30 minutes to run the robot in the arena. We know this was working earlier because we saw their robot move when they during their setup time. So not sure why the robot isn't moving right this second. It did back up a hair. There we go. You can see the front loading bucket moving. You can see the wheels moving now. Again, this Queensland University of Technology team is a demonstration team. This is not a scoring run. This team actually won the Australian Rower Challenge, which is a competition very similar to Lunabotics that is organized and run by the University of Adelaide in Australia. This team calls themselves Team ROAR, and ROAR stands for Remote Off-World Autonomous Robots. There you can see the robot exiting the starting zone and getting through the obstacle zone. The obstacle zone has both rocks and craters that teams are going to want to avoid. And then once the robot crosses this line, it is now in the excavation zone. This zone of the arena is available for digging, for excavation. So now we can see this robot lowering its digging bucket. It looks like they're on top of it. It looks like they want to grab that rock, though. Maybe they changed their mind. They were heading right toward that big rock. Does anybody think that this robot can pick up that big rock? It almost looks like that's what they're going for. Their front-loading bucket, which can be used to scoop up regular simulant, it looks like it could also be used to pick up a rock from above. You'll notice as the wheels spin how soft and fluffy, how light and fluffy the top few inches of this soil is, as I mentioned earlier. So this robot is getting around pretty reasonably in this light and fluffy simulated regolith. Its wheels are spinning a little bit, but it appears to not be causing major issues for this robot. Okay, they're lowering their bucket now. Now maybe they're going to do this smaller rock instead. That is exactly what this Queensland University of Technology team appears to be doing. This appears to be a dual-use implement. Not only is it a front loader, which can scoop up particles, but it's possible that they can actually grab onto rocks from above. It's possible they gave up. It's possible this rock was just too wide for the open mouth of their jaws. But this is a really interesting design that the front bucket implement could open up and create a mouth of sorts with jaws that can potentially grab onto objects. So This Queensland team is pushing the rock, and the rules do state that rocks that are carried or pushed from the excavation zone into the scoring zone will count towards scoring. This is volume. Any volume, either dirt or rocks that are added to our laser scanning zone will count and add to that volume. I just noticed that the students in the control room have actually turned off the two cameras that I was pointing out earlier on the monitors in front of them. So they are completely depending on data from the robot at this point, and are not dependent on data from, at least camera data from, provided by Lunabotics. They're controlling this robot manually by hand using a joystick controller. And that rock is really, really giving them some resistance. Okay, it looks like they might try and pick it up from above now that they've changed the angle of the rock. Maybe they can find a corner of that rock to kind of get a grip on. You can see as the wheels were turning and just then in this zoomed in image how much those wheels were slipping, and that's because the light and fluffiness of this soil, this simulated moon dirt, it's really light and fluffy like talcum powder, at least on the very top several inches, and that does not make it easy to drive on, especially when you've got resistance from some other part of your robot. They're not giving up on this rock though. So if I zoom out, the scoring zone is in between the orange posts. The scoring zone is not the orange line on the ground. The scoring zone is about a foot further than that. So it looks like this Queensland team has at least temporarily given up on pushing that rock into the scoring zone, and they appear to now be performing more of a dozing operation. So they're lowering their bucket and then driving their wheels. Now if the bucket goes too deep, those wheels are just going to slip. It's just not going to have enough power. So they have to find the kind of fine-tune the bucket height in order to push just enough material, because if they go too deep with their bucket, I don't know that they have enough traction. They've got a good scoop there. Hopefully they can get that into the scoring zone. Scoring. So that is scoreable material. Again, this is just a demo run, though. Not actually being scored for this team. But success. We are 10 minutes into a 30-minute run, demo run for Queensland University of Technology. They appear to have changed their tactic from pushing a rock into the in for scoring, and changed to bringing in scoops, one scoop at a time. I will say that these overhead cameras do not really do a great job of showing how much material has been dropped into the scoring zone, partly because the material is all just gray. And yes, thank you for the side camera. This side camera gives a little bit better feel for how much material has been brought in. But I will say that even this side camera doesn't do it justice. Only the human eyeball, when you're standing right near it, can really make out the amount of material that is in there. And I think that's mostly because it's all gray and there's not a lot of good shadows to help you see with these two-dimensional cameras. So Queensland University of Technology continues basically the same path over and over, getting one scoop at a time and dumping it. So their dump mechanism actually opens up their front-loading scoop, which potentially could also be used to pick up rocks if they were of the correct size to fit inside. If we look quickly at the students in the control room, we can see Queensland has put 3 students into the control room. They each have a laptop in front of them that they brought into the control room. And the student in the center is actually driving the robot with a joystick. And the other students are providing support, probably talking about the data that they're seeing on their screens and giving advice. The timer in the upper right-hand side of the screen is the time left in our 30-minute run for this team. You can see the focus. The focus of the student who's driving the robot. You can also see that the other larger monitors that during the setup time did have camera feeds on them to help the students set up the robot. Those are now turned off, so the students for this team have decided to not use those 2 camera feeds that are provided by Lunabotics competition for their event. And you can see in the student's screen right there, they are able to see live camera views directly from their robot right there on their laptop screen while they're driving the robot. That as they continue, they're getting a nice big pile in the scoring zone. There is a bit of a pile just a hair outside the scoring zone that hopefully they can get some of that material into the scoring zone before in the next 15 minutes. So even though this team is not running this robot autonomously, they're basically driving it with a joystick. Even though they're not autonomous, this robot has a lot of sensors that this team is using in order to assist their driving of the robot. Multiple cameras, obviously. Yeah, right there is the material that was just outside the scoring zone that they need to maybe see if they can get that pushed in. It's just too close to not get credit for. So from this angle, we can see that there's kind of a hole right there where the bucket is now, and then it gets higher a couple feet in front of it. The students have a different view. They're looking at onboard cameras, so their view may not be as clear to them as it is to us where the pile of dirt is and where the pile of dirt isn't. This is an area where, oh, they got a good bite that time. This is an area where high-tech 3D sensors can be helpful. Depth cameras instead of just standard RGB visible light cameras can help map the soil in front of the robots and tell you where the low spots are and where the high spots are. Even if they know where the high spot is, it's not easy because the wheels go from going downhill where they start this run to going uphill, and so in order to compensate from the wheels transitioning from downhill to uphill, your arm basically needs to compensate by moving down quite a bit, and that's not an easy thing to coordinate, especially if the speed of the wheels are a lot faster than the speed of the arm. But if they keep doing this, they'll get more and more of that pile that's just outside the scoring zone into the scoring zone. Looks like we have around 100 people watching our live stream right now. Thank you to everyone who's watching, and thank you to everyone in the room who has shared the live stream link with friends and family, and those back at school that weren't able to come. Yeah, now you can see they're really focusing on that pile that is just near the scoring zone, but a little bit outside. But this is the part of the track that goes uphill, which makes it harder to get that dirt, that soil moved. We have 11 minutes in this run. All right, this is pretty impressive. The Queensland University of Technology robot is moving this really, really big rock around. I don't know if they have enough counterbalance mass to actually pick it up, but they're focused on it. They have 9.5 minutes left in their run, and they've decided to focus on this big rock. Which is a pretty fun choice. Definitely have enough power to move it around to make it wobble. Do they have enough power in their robot and enough counterbalance weight to actually move it into the scoring zone though? Maybe they're just that's what they're doing. They're pushing it out of the way to give them a little bit more runway, an area to get out of that old track that they've been driving in repeatedly. Because as light and fluffy as this material is on top, the more you drive in the same track over and over, you can, depending on your wheel speed and whether you're slipping or not, you can actually fluff up that harder material that's below and make it a lot more fluffy, a lot deeper than just a few inches, which can make it harder to perform your operations sometimes. So with 8 minutes left, Queensland University of Technology, for a demonstration run, non-scoring, has lined themselves up again to push material or to pick up material and drop it into the scoring zone. So pushing that material that is just a hair outside the scoring zone may be easier than picking it up, which is kind of what it looked like they were going for there. I guess that's one of the benefits of a front loader bucket, is that not only can you dig a bucket full of material and basically make a hole, but you can also use it as a pusher, a bulldozer blade, which is especially this one that can open up like that. Again, we have a much better view of what's going on than the teams actually have. So it's a little bit unfair for us to be watching this view and say, do this, do that. Why aren't you doing this? Well, we have a much better view. In a lot of cases, we have a much better view than the students actually have from their onboard cameras. A better angle, anyway, I should say, for certain operations. So you can see from this overhead camera, there's a pile right there under the bucket between the wheels right now, the front wheels, that they're having a little bit of struggle getting moved into the scoring zone. It's so close, but not technically in the scoring zone. That little rock, they did end up moving into the scoring zone earlier. Five minutes left for this run for Queensland University of Technology. And then when this run is over, we will go through the motions of performing our official scoring, doing the laser scan. The team will remove their robot as soon as we tell them they're allowed to. And then our next team will start getting ready to come in for their official first run of NASA Lunabotics 2025 finals. First team that's going to run today is Michigan Tech. So Michigan Tech is on deck. Getting psyched up, getting ready to go into the arena as soon as the judges tell them they're ready for them. I should mention that each team will get 2 official scored runs during this competition over today, tomorrow, and Thursday. We have just enough time in the schedule to get all 10 of these teams 2 30-minute runs in our arena. And the scoring for those 2 runs is not the best of 2. It's not the average of the 2. It's the summation of the 2 runs. Yeah, it looks like this Queensland team is trying to get out of those deep tracks that they created earlier and try and slide over next to where they were digging earlier. It's possible that they've fluffed up that material so much that it's getting hard to drive in. That's a nice big scoop there if they can get that into the scoring zone with 3 minutes left. This area right there is kind of hard for the robot to get past. They've actually created a rut in the middle of the excavation zone and a little bit of a hill just outside of the scoring zone. So it's not too difficult for this robot to pick up a scoop down in the low part. But getting all that material past the hill and into the scoring zone is not trivial. So we got a nice scoop here, and you'll see their wheels will go downhill a bit before they start going uphill. Two minutes left in this demonstration run for Queensland University of Technology, a team that won the Australian Rover Challenge recently. 2 minutes left. I think they might be able to get one more scoop in 2 minutes. Let's see what they focus on in their last 2 minutes. That was a really nice amount of material right there. All right, time's run a little short. Are they going to make this last scoop? Minute and a half left. Again, this is another view that the teams do not have. This is a pretty great angle for looking at things like whether wheels are spinning and what the angle is. Oh, they're going to make it with plenty of time to spare. Might even have enough time to go back for one more. Oh, some of it's still holding on. "45 seconds. This is the only planned demonstration run we have on the schedule. So this is the only run that this Australian team is planning to do this week during our Lunabotics competition. They will however, be here in the pits with their robot. So feel free to stop by their pit for those that are in the room and chat with this award-winning Queensland University of Technology team. And as their time runs out, let's give Queensland University of Technology a big hand. It's a great demonstration run for this team. We will go ahead and perform a laser scan and calculate how much volume they were able to move into the scoring zone. They will appreciate having that data. They actually were here early and were able to do a run for us yesterday and help us run through our processes and work some of the bugs out in our process. So I'm sure they'll be happy to compare the score from this run with their score from yesterday's dry run. Now you can see the judges entering the arena and looking at the robot and writing down numbers. They're writing down the energy that was used by this robot during its run, which is part of the final score. If two robots end up creating the same size berm, the same size hill, but one of the robots uses less energy than the other, the robot that uses less energy has a scoring advantage over the robot that uses more energy. Another variable that's quite important is the weight of the robot. If two robots end up creating the same size berm, but one of the robots is lighter, the lighter robot actually gets a scoring advantage in its final score. So these are just a few of the trade-offs that all of these teams that compete every year in NASA's Lunabotics Challenge have to perform these trades when they're designing the robots to decide, are we going to try and come in underweight and get a little bit of an advantage of all the other teams that maybe just hit the weight limit right on the mark, or are we going to go ahead and just hit the weight limit like a lot of other teams and try and find an advantage somewhere else? For example, maybe use less power than other teams, maybe just be faster and end up with a larger pile at the end. All right, as the Queensland University of Technology students removed their robot from the arena, the Artemis Arena, we like to call it, our next team, which is about to enter the arena, is Michigan Technological University, Michigan Tech for short. They will be the first of our 10 teams to perform their first of 2 runs in NASA Lunabotics 2025 finals competition. It will take a bit of time for our arena judges to reset the arena to make it fair for each team. We want to start the arena in basically the same condition for each team. And so we're going to see that happen over the next handful of minutes, and then we'll see the actually that's the Michigan robot right there on camera. So the Michigan team has entered the arena, and so the long pole is going to be resetting the arena. So let's enjoy watching the judges reset the arena. Maybe we'll also get a view of the Michigan students coming into the control room in a little bit and setting up their computers. So don't go anywhere. We have about 100 people watching our live stream. Thank you for everybody who's watching. Continue to watch. Share the link with friends and family. Next up is Michigan Tech. After that, we will have a lunch break that includes award presentations. We will give out the STEM Engagement Award, and we will give out the Presentations and Demonstrations Award. Then after lunch, I believe we're going to have University of Virginia, then University of Alabama, then Milwaukee School of Engineering, then University of Utah, and then Colorado School of Mines. That is not all 10 teams. We will pick up tomorrow morning in order for Purdue and University of Illinois Chicago and University of Akron to run tomorrow morning. All right, so don't go anywhere. You are watching NASA's Lunabotics 2025 finals event, broadcasting live from Kennedy Space Center Visitor Complex here in sunny Central Florida. All right, as you can see, the Michigan Tech University students that had put the robot in the bin are now leaving the bin. So during the first 7 minutes of their 10-minute setup time, the Michigan Tech team appears to be ready to go. What we saw them do on camera during their 10-minute setup time, in addition to setting up their computers in the control room and booting everything up, connecting their networks, they moved the wheels of the robot slightly to verify that commands were working. They moved the digging system slightly to verify commands were working. So students appear to be happy with the command and control and communications and networks, and I think they're ready to go and possibly not need to use the entire 10-minute setup time. And you can see they're turning off the screens in front of them, the larger screens, which implies that they are choosing officially to not use the Lunabotics supplied camera views. They're totally and completely going to be using onboard camera views that are provided to them directly from their robot. It looks like the countdown timer stopped. That's possibly because we're resetting that clock to 30 minutes for this run to start a few minutes early maybe. Again, this is the first run in the finals event for Michigan Tech. It's the first of 2 runs that each of these 10 finalists will get over the next 3 days. You can see the wheels. Oh, and we're going. The 30-minute timer has started, and the robot has already left the starting zone. You can see the obstacle zone from this overhead camera has several rocks in it. I don't see any obvious large craters. I will say that the layout of the obstacle zone is going to be roughly the same for all 10 teams' first run. And then the layout of the obstacle zone is going to change for all the teams' second run. And then be roughly the same for all 10 of those second runs. So this robot, look at the wheel design of this robot. It not only is it a 4-wheel drive robot, but it actually is a 4-wheel steering robot. It looks like each wheel, or at least each wheel pair, has independent steering control. And it looks like they have made it through the obstacle zone, and now they have come into the excavation zone. Now what I suspect this team is going to do is position their robot to be in the direction where it can dig on the side facing away from the scoring zone, and then dump on the side facing towards the scoring zone, which is what they just did. So the scoring zone is on the right of the screen, and the excavation zone is on the left of the screen. There are rocks and at least 1 crater in the excavation zone. So this Michigan Tech team has crossed the obstacle zone rather quickly and are positioning themselves in a position to excavate and transfer material. Now, if we take a quick peek at the students in the control room, we can see whether they are driving this robot with a joystick. Looks to me like they are hands off their joysticks. They're looking intently at their computer screens, and so I suspect this robot is in autonomous mode right now. So it looks like this robot is digging autonomously. So the digging has to happen on the left side, the left quadrant, and then the depositing, the dumping, needs to be within those orange posts in order to count as scoreable material. And that first load, you can see the hole that they left behind. The technology chosen for excavation by this Michigan team is a plunging bucket ladder. A bucket ladder that can, it's a bunch of digging buckets that are attached by a chain, almost like a conveyor belt system of digging buckets. But the whole system can actually be plunged down deep into the ground in order to get into that really dense stuff below the surface. And I mentioned the four-wheel steering. That can give this robot pretty unique mobility options. It can kind of stray sideways. It can spin in place. Not only can it spin in place, but its wheels go diagonal when it spins in place, which keeps it from really digging in by the sides of those wheels. So when you see an autonomous robot pause like this, the students have an opportunity to decide whether to step in and go into manual mode, or whether to let the robot continue to think and process in hopes that that they won't destroy the chance of autonomy points by stepping in too early. So it looks like the students are still not holding their joystick, so it looks like we're still in fully autonomous mode. And it looks like the sensors that this robot uses are depth cameras. There's one on the top right, the front right corner of the robot, and there's one centered on the back of the robot. So the camera in the front can basically tell this robot where the obstacles are, and the camera on the back can, in theory, tell the robot where the scoring zone is. And this is their second cycle of digging and dumping. This robot is long enough that it only has to drive about a foot or so between the excavation side and the offloading side. That can potentially give them a little bit of a time advantage over robots that have to drive further. You can see how their conveyor belt slowly moves forward. This is actually the camera that the students could use if they chose to. Not this one, but the one that we just had on the screen. It's just one of our pan tilt zoom cameras in the arena. You can see their conveyor belt moves slowly in order to kind of spread out the material on board as it's digging. Okay, the student just took control of the joystick. They did get a certain amount of autonomy points for repeated cycles, I believe, according to the rules. But now I noticed the student in the control room, 2 students, each with a joystick, and so I presume one of the students is driving and one of the students is operating the digging equipment. So with 20 minutes left in this run, looks like the rest of this run is going to be manual control. The students have not turned on the 2 optional Lunabotics event supplied cameras, arena supplied cameras. So they're sticking with their onboard cameras, but they're stick driving this robot now, probably till the end of this run, I would suspect. So you can see when they're manually driving this robot, they're being more aggressive, and that doesn't surprise me. If I was writing automation software, I would make it pretty conservative. But you can see they're really pushing this robot, trying to take this manual time and just maximize the volume of material that they collect. So I think we'll see probably when this one offloads, we'll probably see this was a bit more material than earlier when they were performing autonomously. Some of that material is outside the scoring zone, sadly. Not a lot of it, but it makes you realize that the students don't have this beautiful overhead view that we have. They chose not to use, because it gives them a scoring advantage. They chose not to use our overhead camera that we allow them to optionally use. And one of the trade-offs there is you may not have the visibility that you want. Hopefully this ends up being a good decision and they still end up with the amount of material that they really wanted to get on not just on board, but delivered into the delivery zone. Again, there's another manual run, and being very aggressive. Pushing that digging implement down as far as they can and just driving that robot forward, and their conveyor belt taking it all the way to the edge. Matter of fact, a little bit of their potential material that could have given them some score has dumped out the back, but not very much. The brunt of the material is still on board the robot. Side view should show us, kind of sort of shows us that some of this is a little bit outside the scoring zone, outside those 2 orange poles. Again, this is Michigan Tech. Up in Michigan's Upper Peninsula, these teams have driven here all the way from Michigan's Upper Peninsula. They've chosen a 4-wheel drive robot that also has 4-wheel steering, which gives them more mobility for getting around tight spaces, which can sometimes be an advantage in this competition. They chose a plunging bucket ladder system and an onboard conveyor belt to hold the material and then dump it. They chose a kind of an opposing style where the digging happens on one side of the robot and the dumping happens off the completely opposite side of the robot. That can be slightly advantageous as far as not having to turn your robot around, not having to drive as far. Will these design choices pay off for Michigan Tech, though, compared to the design choices that some of these other teams have chosen? I kind of wish they would back up a little bit more, but I guess they don't realize that a lot of this material is outside the scoring zone. I said a lot, but it's actually hard to tell from this angle. I could be wrong. But those piles are significant. Even from these cameras, which, you know, have a hard time giving us the contrast we need to see big piles, they still look like they're pretty decent sized piles. I'm no expert, but that's at least a 5-gallon bucket's worth, right? I think they're probably going to be happy with that. And boy, so much time left. Still 16 minutes left in this first of 2 official scored runs. Oh, the front wheel went into that hole from earlier just then. Look how deep that front wheel is. But even with only 3 wheels touching, doesn't look like they're having any trouble driving. You'll notice this robot's wheels are not slipping and spinning like we saw earlier. The traction, though, they're going. They're going all the way into the middle of the scoring zone. So this is all scoring material. Some of their material, I was about to say some of the material is slipping off the conveyor belt, but I was wrong. Now you can see them sliding to the left, so they're not on the same track. Earlier, just a minute ago, we saw one of their wheels go into a big hole. I wonder if this is going to alleviate that. They definitely need to pick a new spot each time for digging. I did earlier call this a plunging bucket ladder, but I think technically it's a rotating bucket ladder. I'm not sure that it has linear actuators that are actually drawing it down. I think it's just rotating. I should have done my homework. So for those in the room, a quick lunchtime award ceremony is going to happen at the end of this run. We're going to give the STEM Engagement Awards, and we're going to give the Presentations and Demonstrations Awards after this run. So about 15 or so minutes from now, make sure you make your way down to the stage side of the building. Also, there's a astronaut man photo opportunity for those in the building over here by the stage. Meanwhile, this Michigan Tech team is getting a good pile of material. And you can see how big the holes are that they're leaving behind. Looks like most of this load is going to be just inside the scoring zone. Yeah, I think they're going to be happy with this, even though some of their material is ending up outside the scoring zone. You can see it says student driver on the back of this robot. That's funny. This side view gives you a better view of the material that's inside the scoring zone. You've got kind of 3 or 4 different piles there. If we zoom in on their buckets, we can see some detail. They've got these sharp teeth. You can see it rotating there. The wheels are driving forward slowly while they're digging. Conveyor belt is moving forward while they're digging. I don't see hardly any wheel slippage. By the way, NASA has a team that is studying these robots during this competition all week long, and they were even at UCF studying them there last week, studying wheel slip and wheel design. And NASA takes full advantage of these competitions and learns as much as we can from these competitions. And so we're taking lessons learned from even collegiate competitions like this in order to take what works, understand what works and what doesn't work, and take that knowledge to the moon someday. So there's a lot more benefits to a competition like this. The more you learn, the more you realize so many benefits. Oh wow, that is a really deep hole. This robot didn't even flinch. This robot didn't even flinch at that hole. It just kept on driving. They got 10 minutes left, and they're like, hole? What hole? I mean, the students did that. The students drove that robot there. Can't say that was an automation mistake. The students did that, but they were not scared of that hole. They knew that their robot had the grip, the strength to get through that hole. So having the grip and having the strength, is that what it takes to win this competition? Well, as I said earlier, there's a lot of variables. One of the variables is efficient use of power. A robot that can do this kind of work and not use a lot of power, they are definitely going to have a scoring advantage. So this Michigan Tech robot appears to be strong, but is it efficient in its power usage? Only the judges know when they collect their data. So much time remaining, almost 9 minutes, plenty of time to get a lot more material. I should mention it's probably obvious, but as these robots load up the material, they get heavier. And in some cases, that can give the robot extra grip, but in some cases, that can actually cause issues and make it harder to drive on this surface. But this Michigan Tech robot appears to not have excessive slipping, regardless of whether it's empty or full of material. So there's something about the design of the mobility system that is really working excellently in our simulated lunar soil. Oh man. Students did not even blink. I'm looking at the students in the control room. They did not even blink. They still haven't even blinked. They are focused on driving this robot. I guess they were trying to get in the corner there. They're still trying to get in the corner there. The students are not panicking. One of them is laughing. The driver's not laughing, but they are focused. Okay, they gave up. Okay, they're backing out. That is good job. Yep. Okay, now the driver's laughing. The driver is relieved that he got out of that spot. I mean, honestly, if they did get stuck there, I think they'd still be happy with their score, right? They've got a look. They've got a nice pile there. Don't drag any out accidentally. They in their last 7 minutes, they need to find a new spot to dig. A spot that is not at risk of getting them stuck. Because this is a pretty efficient as far as cycles per hour, I guess. This robot is going back and forth and back and forth and back and forth pretty quickly. So they can still do a lot of work in these last 6 minutes. It's a good view from overhead of the hole that they've created right there. Wish I could move that particular camera, but I cannot. That happened to be the camera that only the students control if they choose to do so. All right, this is a little bit turn in place. Are they showing off a little bit now? Or are they legitimately trying to find a new spot to dig? Shows off their four-wheel steering. Okay, they found a new spot to dig. They're basically creating a fan-shaped dig site. And looks like they've spread out their digging holes in such a way that they will make it all the way through their 30-minute run without running out of places to dig. If I can zoom in on their digger right now without messing up the camera. Oh, I missed it. I was gonna point out how tough this material is. You can see you'll see gravel and rocks. Oh, they're going backwards. I'm not sure. Maybe something got stuck or hung up for a second, so they had to run it backwards to unstick it maybe. Those digging buckets are each pretty deep. So they're capable of pulling up a lot of material into those buckets. 3.5 minutes remaining. Looks like they're going to line up for another deposit into the scoring zone. And with 3 minutes remaining, they'll have plenty of time to do at least one more cycle, if not two. It's a good view of how much material was on board just then. The student drivers are doing a great job. Just under 3 minutes remaining for Michigan Tech's first run of two. Kind of in a zone there where there's some holes that they need to be careful of. Oh, they're going way, way out in the far end of the dig field. Picking a spot. Camera 2 is kind of fun. It shows one of the wheels, the back wheel, just kind of nestled in on that rock there. If they needed to go further south, further down, that would be not easy. But going backwards up towards the top of the screen shouldn't be a problem for this robot, I don't think. Sorry, there's some structure in the way in this video. They are driving forward while digging and driving over that rock without even blinking. It's possible their onboard cameras are not showing them about that rock there. It's also possible that it did show them and they don't care because they know their robot is capable of digging while driving over that rock and not caring. So they're driving back very slowly. Maybe they are worried about that rock a little bit. Okay, they're down to 38 seconds, so this is probably going to be their final deposit of material. There's that rock again. The front wheel's about to go over it. It makes you wonder how much the students are aware of that rock. Seems like they know. Seems like they know. Or they at least know something's up there. All right, in the last 10 seconds, this team should be able to get deposited into the scoring zone. And with that, Michigan Tech, that's their first run. Let's give them a big round of applause. Their first run of 2. Great job, Michigan Tech. You should be proud of that. In addition, we did see on the screen that they did appear to be going for some autonomy points, even some repeated autonomy points, which are a bonus there. So as the Michigan Tech team recovers from their run, here in the pit area, we are going to have a quick award presentation. We are going to give the STEM Engagement Award, and we're going to give the Presentations and Demonstrations Award. So if you are in this room, come on down to the stage area of this room because you don't want to miss the award ceremony. You might actually miss an award given to you. So come on down and encourage the teams who are winning these awards, the STEM Engagement Award and Presentations and Demonstrations Award. We are also going to take, I think, an hour break. Pit boss, are we taking an hour break, pit boss, for lunch? I don't think she can hear me. The schedule shows an hour break for lunch, but the pit boss knows who's up next is University of Virginia, and she will tell University of Virginia when to get ready for their run after lunch. So stand by for just a few minutes for a quick award ceremony right at the beginning of lunch. You are watching NASA's 2025 Lunabotics Finals competition here at the Kennedy Space Center Visitor Complex in sunny Central Florida. Don't go anywhere.
Across the nation are sacred sites that capture the spirit of America's character. And one of those places is right here, the Kennedy Space Center.
Every single vehicle that has carried humans beyond the bounds of low Earth orbit has undergone integration and testing in that vehicle assembly building, crawled down this roadway and launched right here from the Kennedy Space Center. The Space Launch System, mated with the Orion spacecraft, will continue this proud tradition.
As soon as we roll out of the vehicle assembly building, High Bay 3, and the world gets a chance to see this rocket, I think it is going to be shocking.
On March 17th, NASA took a giant step toward returning humanity to the moon. The fully assembled Space Launch System rocket and Orion spacecraft for the Artemis 1 mission made its debut outside the massive vehicle assembly building.
We've seen the mobile launcher outside, and it's massive, but now add an over 300-foot rocket on top of it, it's just going to be amazing.
Charlie Blackwell Thompson oversees the launch countdown, ultimately providing the go for launch.
Entity, launch director, representing this team and all the men and women that have worked to make this day happen, I proudly give you a go to roll the Artemis launch vehicle to the pad.
Ladies and gentlemen, the world's most powerful rocket right here.
Once outside, the rocket began its nearly 4-mile journey to the pad, riding atop a 6.6 million pound crawler transporter, which was originally constructed to transport the Apollo moon rocket.
In 1 year, we have completely stacked the vehicle. We completed most of our testing, all very successful, and we are so close to launch, and the excitement is just crazy.
Now NASA's new moon rocket is making the same journey the Saturn V took 50 years ago.
And just as all eyes are on the SLS tonight as it makes its journey, in a few short weeks, all eyes are going to be on the sky as it rocks the space coast and takes its maiden flight around the moon.
It is amazing to see the culmination of all of this work of many years from many industries and many people that have come and go, to have a chance to then now see their work going over to the pad and then launching to go to the moon.
The rocket is rolling to historic Launch Complex 39B, its launch pad used for both Apollo and shuttle launches, sending hundreds of astronauts to space throughout the decades, and now on tap to send hundreds more as we return to the moon and venture beyond to Mars. But for this mission, there will be no astronauts on board. Before the uncrewed Artemis 1 stack can launch to our nearest celestial body, it has to travel to the pad for a wet dress rehearsal, a test to run the rocket, capsule, launch team, and launch pad through their paces, simulating a launch countdown.
When we get to the pad team will be connecting all the interfaces between the pad and the mobile launcher so that we can go ahead and start our operations at the pad. So at that point, the launch director really takes over, and she will go down the sequence as if it was really a normal launch day.
Wet dress rehearsal is essentially launch without a launch. It is really the reason we're doing it is to verify and validate all of the pieces that go into launch countdown. So wet dress is really our opportunity to find any issues or adjustments that we need to make in our launch countdown.
For Artemis 1, the wet dress rehearsal is the final and most critical test before the rocket can return to the launch pad for liftoff to the moon. During the countdown, over 730,000 gallons of supercooled liquid propellants will be loaded into the rocket as part of the nearly 2-day launch countdown.
We will configure all of the ground systems exactly the way we would for launch, and we will fully load the core stage and the interim cryopropulsion stage with their liquid fuels. That'll be the first time that that's been done from here at Kennedy Space Center. There have been pieces of these things done in multiple different areas. We've tested all of these systems in multiple different locations, but this will be the first time where we pull it all together into all of it, all in the same progression that we've we've got laid out for launch countdown.
Wet dress is the biggest milestone we have aside from launch, because that means that the rocket is now put together, has been tested separately and together, and it is ready to go and be filled with fuel to simulate how we're going to do it at the pad, and then it tells us the rocket is ready to go for launch.
And behind that wet dress rehearsal is a launch team made up of hundreds of engineers monitoring each system of the 320-foot tall Artemis 1 rocket and capsule. Sitting in firing room 1 is the core launch control team, monitoring hundreds of launch commit criteria to ensure the ground systems and flight hardware are ready for launch.
Now you would think that launch control team in firing room 1 is it, that's all you need. We have an expansive support team across really the entire NASA enterprise that is supporting us on launch day.
And that support spans the entire nation, from additional systems engineers sitting in Kennedy's Firing Room 2, to the flight control team at Johnson Space Center in Houston, to the contractors responsible for designing and building each segment of the rocket and capsule.
This team is really shaping up to be a great, very skilled and ready to operate and execute launch for Artemis 1.
With the Artemis 1 launch team now fully certified and the wet dress rehearsal complete, SLS and Orion are ready for their final pit stop, returning to the VAB before venturing back to Launch Pad 39B for liftoff.
I mean, we are going, and we're going together, and we're having an opportunity to do this in a new generation of space exploration in which I can say that I'm honorably a part of.
You know, you come every day to the VAB and you see the rocket and you can't believe what we have accomplished.
People throughout history have always explored, and you never know what you're going to learn.
Exploration is not always about the destination, but it's the path that you travel, the things you learn along the way.
And the things we're going to learn are going to be incredible. We can't even begin to understand what those are today.
Our workforce has been a relentless spirit. We imagine, we build, we never stop pushing the envelope of what is possible.
Hello, teams in the pit room. And hello, those watching online. Thank you for sticking with us. We're going to do a little mini award ceremony. We're going to do a small ceremony at lunch every day. That will make our final award ceremony go a lot quicker and be more focused. So the award we are giving away first is the STEM Engagement Award. So we're here celebrating something just as important as the innovative robots that we've designed. We're here to celebrate also the remarkable work that our teams have done to inspire the next generation of STEM professionals. Because this competition isn't just about creating cutting-edge lunar technology. It's also about sharing our passion for space exploration with students who will one day join our ranks, or perhaps even lead missions to Mars and beyond. The ability to inspire the next generation is a vital responsibility in technical fields. It requires creating personal connections that inspire young people to pursue technical careers. It requires technical knowledge, creativity, and the ability to adapt content across educational levels. So we're going to give awards for teams who have proven that they have done tremendous STEM engagement in their communities. Our third place team excelled through impactful high school presentations that combined technical information about NASA's Artemis mission with personal educational journeys. Their hands-on wheel design activity challenge students to understand the unique mobility issues on the lunar surface while applying engineering design principles, inspiring many towards STEM careers. I am pleased to announce that Embry-Riddle Aeronautical University's Team Moonwalkers are the third place winner. Are there any Embry-Riddle Aeronautical University students here in the room who would like to come up and get their photograph taken with our project manager, Rich Jonabeck? They're probably out exploring the visitor center. We'll get their picture later, Rich. Now, our top two teams are getting the Pay It Forward Award, in addition to plaques for winning STEM engagement. The Pay It Forward Award is given to teams that best conduct impactful educational engagement events in their community or further than that. Educational engagement includes instructional hands-on activities where participants engage in learning a STEM-related concept by actively participating in an activity. Each challenge activity that was led will choose the top teams. Each challenge activity lead will choose the top teams, have chosen the top teams from each challenge for consideration of final awardees. So, both our second place STEM engagement winner and our first place STEM engagement winner are getting these additional Pay It Forward awards. And the Pay It Forward awards are amazing because they come with a flag that was flown aboard the Artemis 1 mission, an actual space-flown flag. This is not a sticker. This is not a patch. This is an actual flag that flew in space. So both of these next two teams are going to get that. Our second place winner for STEM engagement, they mentored first Tech Challenge teams and they developed engaging presentations on the Artemis program and lunar exploration, complemented by activities like building lunar landers and launching paper rockets. Their programming reached students from elementary through high school, and their plans to develop a miniature Lunabotics challenge shows forward thinking. Anybody think they know who it is? I'm pleased to announce the University of Virginia's Mechatronics and Robotics Society as second place winner. Come on up. Bring your whole team right over here to get your picture with Rich. We will be giving you a plaque that goes along. Go ahead and head over there for a picture. We don't have the plaque here today, but you will get a plaque in the mail, I presume. University of Virginia. Squeeze in tight, squeeze in tight. Make 2 rows if you have to. Turn sideways if you have to. They were not ready for a photo. I should have probably warned them. Sorry, that's me. That's on me. We have multiple cameras, so their shirts are black on the black background. All right, University of Virginia, 2nd place for STEM engagement. And now for our 1st place STEM engagement award. What does educational STEM outreach look like? It's creating engaging presentations that can hold the attention of middle and high school students while teaching them about robotic systems and programming concepts. It's developing interactive activities where students can apply the scientific method to engineering challenges, and it's demonstrating the ability to translate complex technical knowledge about space exploration missions into content that inspires the next generation of engineers. The winning team exemplified these qualities through their innovative hands-on activities like their Racing Robots program and circuits workshop. Anyone? They designed terrain courses and provided 3D printed components for students to experiment with wheel designs and soil mechanics. Which demonstrated the kind of technical communication skills that every engineering student should aspire to develop. Their approach allowed students to test different solutions and even iterate on designs. With the team, sometimes 3D printing improved wheel designs for future events. The team's circuit building activities culminated in Jeopardy-style assessment games, showing their thoughtfulness in evaluating learning outcomes. Anybody know which team I just described? I am pleased to announce the University of Utah's Utah Student Robotics team as 1st place for STEM engagement. Come get your space-flown flag and come get your picture taken over here. Your whole team, come get your picture taken over here with project manager Rich Johnnebeck. More black shirts. We didn't think this through, did we, Rich? Who knew all the teams were going to wear black shirts? All right, they're going to get their picture taken in a little bit, but let's give them a big round of applause for winning 1st place for STEM engagement, and congrats to all 3 teams for their STEM engagement accomplishments. Thank you for inspiring the next generation to pursue STEM careers. Squeeze, 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 squeeze. 2 rows if you have to. All right. Congrats, all 3 teams. All right. STEM engagement is so important, and the results, you can't even imagine the downstream results for decades, possibly. All right, now we're going to do presentations and demonstrations awards. First, we're going to give a First Steps Award, and the First Steps Award is for the best presentation by a first-year team. How many first-year teams do we have in here? Raise your hand if you're a first-year team. Well, the winner of that award, oh, they're not in this room, I'm sorry. It's the University at Buffalo. Are they in this room? Anybody from University of Buffalo in this room? All right. If they're in Florida because they were at UCF last week, so maybe later we can get our picture with them. So again, we don't have plaques to hand you today, but you will get plaques. Is this correct? Plaques will be in the mail. We're going to give first, second, and third prizes for presentations and demonstrations, but we have an honorable mention. The honorable mention for presentation and demonstration goes to the University of Alabama. You want to do a photo? Do you want to do a photo, University of Alabama? Are they at lunch? They're right there. They weren't even hiding. They were right there. Congrats, University of Alabama. Now, for third place for presentations and demonstrations, University of Miami. Is anyone here from the University of Miami who would like to get their picture taken? Are they in the room? I heard a yell. Was that a happy yell or? All right, second place for presentation and demonstration. Colorado School of Mines. Come up here and get your picture taken. Come get your picture taken with our presentation and demonstrations judge, Rebecca Mazzone. Once again, black shirts on a black background. On your way out, we'll take votes on what color you want the background to be next year. All right, this is it. The final award for this award ceremony today. First place for presentation and demonstration is going to be given to the University of Utah. Come on over. Congratulations. They are psyched. This is a big team. We need 2 lines at least. Tall people in back. You know the drill. And Pit Boss, if you can hear me, Pit Boss. It would be nice to announce at the end of this award ceremony what time our next team will run. Thank you, Pit Boss. So stay tuned for an announcement of what time our next team is going to run, which is Virginia, right? Am I remembering right? Virginia, they're ready. We're going to take a break for lunch and keep listening. Yeah. Oh, yeah. Well, what are they? I don't have it in front of me. Tomorrow's awards during this lunch break are going to be system engineering papers, so get excited for that tomorrow. So that concludes our mini awards ceremony. Enjoy your lunch, and make sure you are back in time to watch Virginia run, which will be announced here soon.
What President Kennedy said was, we choose to go to the moon and do other things, not because it's easy, but because it's hard.
The cost of failure is much higher than the cost of scrubbing. We have an obligation to get this right.
This is a whole new vehicle, a whole new technology, a whole new purpose of going back to the moon in preparation to go to Mars. And yes, it's hard.
The countdown to T-0 starts approximately 2 days before launch. Teams inside the Launch Control Center have been working around the clock, powering up each section of the rocket and configuring the launch pad to support the 8.8 million pounds of thrust our moon rocket will generate at liftoff.
It is a new creation. It is a new rocket and a new spacecraft to send humans to the moon on the very next flight.
Today, we make history. With the launch of the most powerful rocket the world has ever seen, we are taking the first step in humanity's return to the moon.
I can tell you there's an energy and there's an excitement around the Kennedy Space Center, I would say, across the agency and all around the Space Coast as we get closer and closer to this launch.
This mission will validate that the rocket and capsule do perform as expected before future Artemis missions send astronauts to the lunar surface.
We have worked really hard to get here. The team has done an absolutely outstanding job, and we're up to the challenge, and I'm really looking forward to a successful test flight.
You are looking at the world's most powerful rocket and Orion spacecraft live on Launch Pad 39B. Artemis 1 embodies the hard work of thousands across the world, determined to explore for the benefit of all. I'm Megan Cruz, and this is NASA astronaut Kayla Barron.
When I first walked up and saw the view from the desk here, I was just blown away.
This is the moment when it comes to the countdown, and then tension starts, and well, let's cross fingers everything works well. Tension is rising, and we are fully excited here.
Over the past few years, teams have put in thousands of hours, performing simulations and rehearsals to ensure that they are ready for this moment.
As our 0 hour approaches for the Artemis generation, we do have a heightened sense of anticipation, and there's definitely excitement amongst the team members. We've noticed just the overall mood and focus within the team is definitely a positive one.
Now, with all systems configured correctly, the launch director gives the final go for liftoff.
On behalf of all the men and women across our great nation who have worked to bring this hardware together to make this day possible, and for the Artemis generation, this is for you. At this time, I give you a go to resume count and launch Artemis 1.
This mission goes with a lot of hopes and dreams of a lot of people. It's no longer the Apollo generation. It's the Artemis generation. That brings a whole new world of discoveries.
T-minus 50 seconds and counting. The Space Launch System is now counting down to liftoff of Orion on its maiden voyage to the moon. And here we go.
10.
Hydrogen burn-off igniters initiated. 7, 6, 5. 4-stage engine start. 3, 2, 1. and liftoff of Artemis 1. We rise together, back to the moon and beyond.
Well, if you're just joining us, welcome to NASA's Kennedy Space Center, where we just watched Artemis 1 launch, our first step towards our next adventure into deep space.
With Orion off the ground, Mission Control in Houston takes the reins. Our nation is returning to the moon.
And we have worked hard as a team. You guys have worked hard as a team for this moment. This is your moment. It is not by chance that you are here today. So I want you to look around at this team and know that you have earned it. You have earned your place in the room. You've earned this moment. You have earned your place in history.
The successful launch of SLS is just the beginning. Orion will spend the next several weeks journeying around the moon, sending flight data back to teams here on Earth for real-time analysis. During its mission, Orion reached speeds traveling about 30 times as fast as the speed of sound.
This dramatic video of the Earth-Moon transit that took place showed and punctuated the fact that we were pressing away from our home planet to a distance of some 268,000 miles away from Earth, further than any traveled, for a spacecraft designed to return humans to Earth, eclipsing the mark set by the Apollo 13 vehicle back in 1970.
After several weeks of flight, it was time for Orion to return home.
A half-century later, NASA's newest moon explorer, the Orion spacecraft, is barreling its way back home after circumnavigating the moon and beyond in an elliptical distant retrograde orbit. Now less than 2 hours away from splashing down in the Pacific Ocean west of Baja, California, to complete its shakedown mission.
Like the Apollo missions of the past, Orion will have to endure incredibly high temperatures during re-entry of Earth's atmosphere.
A journey that began with the power of the launch of the Space Launch System 25 and a half days ago, about to reach its final minutes in the searing heat of re-entry, where temperatures around Orion will build up to 5,000 degrees Fahrenheit.
While re-entering Earth's atmosphere, the spacecraft slowed to about 300 miles per hour. As it continued its descent, Orion's parachute system, containing 11 total parachutes, deployed once it reached approximately 9,000 feet and a speed of about 130 miles per hour.
And there it is, high over the Pacific, America's new ticket to ride to the moon and beyond now in view. Orion under its chutes descending toward splashdown.
These parachutes help slow the crew module to a much more manageable speed, roughly 20 miles per hour, for a water landing off the coast of California.
Splashdown. From Tranquility Base to Taurus Littrow to the tranquil waters of the Pacific, the latest chapter of NASA's journey to the moon comes to a close. Orion, back on Earth.
We've got a perfect view, a front row seat to the Orion splashdown. And it's simply beautiful out here. That is a human-rated capsule that went around the moon and returned and is now in the Pacific Ocean.
I think I can speak for the whole dive team that we're honored to be part of history and to be part of something so monumentous, and just ready and excited to go out and do this.
When Orion was deemed safe to approach, team members jumped into the water and attached hardware that steadied the capsule.
What we do at NASA really is all about collaborations, and the collaborations that we've had with the Department of Defense in particular over the past many years, their hard work and their dedication as they went through a great deal of planning, hardware development and processes, and a lot of practicing to get to this point and make it look easy.
And that team, made of a combination of NASA and Department of Defense personnel, has put in years of work to make sure that they were ready.
Melissa Jones, the recovery director, just came from outside the ship's control center where she was monitoring and, of course, managing her team in the midst of this recovery. So, Melissa, thank you for being here.
Thank you for having me. It's been a long time coming. We've been working this mission for a while, and we've done a ton of training. And every time you do training with a mock-up capsule, you don't have any of that. You don't have parachutes. You don't hear it coming back to the atmosphere, the sonic booms and all of that kind of stuff. And today that actually happened. It's just amazing.
This mission, this spacecraft and this team exceeded all expectations. For the last 25.5 days, we've been every day looking ahead to the next flight to see how we can improve on where we are today so that we can fly a safe and successful mission with our astronauts next time around.
Once stabilized, the team secured the spacecraft with hardware and rope assemblies and towed it to the Navy ship. The dive team then connected Orion to a series of ropes from inside the back of the ship, known as the well deck, to safely and securely pull the capsule inside. With Orion safely secured inside the ship, teams made their way to Naval Base San Diego, where the capsule was offloaded and prepped for its cross-country trip back to its home base, Kennedy Space Center.
This is really the start of a campaign of several missions to get humans back to the moon and beyond to Mars. So there's still a lot to be done, and this is just the beginning.
Kennedy just stunned everybody with the Apollo generation.
I believe that this nation should commit itself to achieving a goal before this decade is out.
And said that we were going to achieve what we thought was impossible.
Of landing a man on the moon and returning him safely to the Earth.
Many things have happened since, but we knew we were going back. This is the program of going back to the moon to learn, to live, to invent, to create in order to explore beyond. Oh, it's a new day. A new day has dawned. An Artemis generation is taking us there.
Did you know there's been over 1 million registrations in NASA's virtual guest program since May 2020? From your neighbor to the Crew 5 astronauts, you might be surprised who is a NASA virtual guest.
Do you have Mars 2020? I do. Do you have James Webb? Sure do. Do you have Crew 5?
Well, I've got it here, and you guys have it here, but I missed it here.
We conducted over 200 science experiments and technology demonstrations on our mission. We loved being part of Expedition 68. We even remembered a virtual guest passport for Einstein, our freefall indicator, but we forgot to register. I missed the stamp.
Even if you're doing existing research, never miss a stamp from NASA's virtual guest program. Whether you're en route to the International Space Station or located anywhere around the globe, register at nasa.gov/virtual guests to receive updates on missions and milestones. As a virtual guest, you will receive curated resources and a stamp for your passport following a successful launch.
Remember, you only get the updates and stamp if you register.
I joined. I won't miss it next time.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills.
It's been 50 years since we've been to the moon, and we've got a great program called Artemis. We're going back. The Apollo program was a test for the American people that you can do what you set out to do. All it took was turning to it and making it happen.
We are go for a mission to the moon at this time.
Engines on 5, 4, 3, 2, all engines running. Launch commit, liftoff. We have liftoff 49 minutes past the hour.
I think the characteristic that I remember most of the Saturn V was the noise. The noise was enormous and it was almost impossible to communicate.
We're go, swing tight, we're go.
Tranquility Base here. The Eagle has landed.
The landing to me was a great celebration. The nation was almost euphoric.
That's one small step for man, one giant leap for mankind.
There are so many things that we could eventually learn about our universe and the spacecraft that we use exploring.
We are a nation of explorers. During Apollo, we were on national TV literally every day because we were doing something visible that Americans could see and they could feel and say, look what we are doing. And I believe Artemis is going to come up and say, look what we are capable of and what we are doing now.
Artemis will stand on the shoulders of Apollo. They're going to have the eyes of the world on them when they start down this trail.
The science of a space flight is one that will continue to inspire. Going to the moon generates technology, more communications, more computer technology, more sophistication in manufacturing that help us in everyday life.
We have a generation that is ready, a generation with that technology, a generation with the education. Artemis represents the future in space. It is our next big step, and it is time to take it.
crawler transporter is it's a machine that goes and picks up the mobile launcher, the SLS rocket with Orion. It's basically the cornerstone of the mobile launch concept. Without the crawler, you couldn't transport the mobile launcher and the vehicle from the VAB to the pad or the pad back to the VAB. And it was designed and built for the Apollo program to move Saturn V's to the launch pad. Since then, we've modified it and used it to move the entire shuttle program. And after the shuttle program, we did extensive modifications, and now it's to be used to move Artemis to the launch pad. The crawler is 136 feet long from end to end. It's 114 feet wide from the edge of the truck to the other edge of the truck. It weighs 6.6 million pounds. It has the power to do 2 miles an hour, but you never want to go that fast. Generally, we're around 0.83 for SLS. Artemis will be one of the heaviest loads we've ever carried and one of the tallest loads we've carried. I am exceptionally proud of our team. They're very talented, they're very committed, and they're just all around good team. I think any problem that crops up or anything that comes up, we'll fix it and we'll get moving again. And again, it starts right here with the crawler. So if we do our job and everybody else does theirs, man, we're gonna have a successful launch. We're going back to the moon. This is gonna be just fantastic.
The imagery that we're collecting on Artemis 1 and the mission itself is preparing to carry humans to the moon. The Orion Imager team is going to be monitoring every aspect of visual spacecraft performance for the entire duration of the mission. The first time that we're going to be live streaming digital video from a human piloted spacecraft back down to the Earth from the vicinity of the moon. That's never been done before. What we'll be transmitting live streaming will be lower resolution, more compressed, because we have to fit it into a thinner pipe, if you will. Every one of these cameras is in its position where it is and it's configured the way it is for a very specific reason. We're going to be monitoring anything that we can see with the cameras for spacecraft performance. The imager teams at NASA are composed of dozens and dozens of very highly trained, very specialized people, engineers, technicians, analysts. If we can see it, we're going to try and keep an eye on it. Imagery has been invaluable throughout the history of NASA. We flew cameras on Mercury, Gemini, Apollo, all of that stuff that we saw with the astronauts around the moon. It helps us detect the unknown unknowns. It allows us to see things that we didn't anticipate happening before. So when we do fly people on Artemis 2, we can have a high confidence that everything is working the way it should.
Our moon. It seems so close in the night sky, but getting there is really hard. But what if there was a way to change that? Only a few nations have successfully landed on the moon. As NASA sends astronauts back to the lunar surface, this time to stay, we will need to send science and technology instruments ahead of time to lay the foundation for human exploration. To make this happen, NASA is helping establish a commercial lunar economy. For the first time ever, there will be commercial delivery services to the moon. We are enabling American companies to send our payloads to the lunar surface for us. These delivery services will expand our capabilities for exploration, radically increasing the amount of science we can achieve. This high-risk, high-reward initiative will invest in and leverage the entrepreneurial spirit of American innovation to launch a commercial lunar marketplace, advancing technology and exploration for all of us. With this never-before-seen streamlined access to the moon, we will be able to make novel measurements and develop technologies that scientists have long wanted to do on the lunar surface. And as this new industry matures, this commercial delivery service for NASA and other customers could expand beyond the moon to other destinations in our solar system, and we can learn to live on another world because we are explorers.
Hi, I'm
return safely to Earth. Meanwhile, we are launching missions to the International Space Station, continuing the research that helps us solve problems on Earth while proving capabilities we need for long-duration human space exploration. Microgravity, low Earth orbit offers a unique environment to study disease formation, test diagnostic tools and treatments, and advanced technologies like computers and robotics. NASA and our commercial partners are expanding the ability to launch crews, science, and cargo to the orbiting laboratory, which will ensure sustainable operations on the station for years to come. Nearby, in the Space Systems Processing Facility, teams are developing other exciting technologies we will need to live and work on the moon. Plant researchers are experimenting with new ways to grow food in space, and engineers are working on projects like 3D printing capability to build structures on the moon, rovers and instruments to find resources to help sustain a long-term presence, and electrodynamic dust shield technology that can repel the abrasive moon dust to protect our astronauts, their vehicles, and sensitive equipment. NASA's commercial providers help us launch a range of science missions that study our Earth, explore other planetary bodies, and reveal more about the orbit
This is really cool. We got some children that are on a bus, and they're going to come here to the vehicle assembly building, and the administrator and I are going to jump on the bus and surprise them.
We're going to give them the opportunity to come in and go up the elevator with the rocket.
It's so cool! Whoa. Look at that thing! Whoa, that's awesome!
Hey guys, would you like to see a moon rocket?
Yeah!
Because it is the future of our country, indeed the future of the world. And we saw what our space program does for science and technology and engineering and mathematics. We saw that in the Apollo generation.
All right, guys, what do you think? What I hope to achieve today is inspiring a new generation. I mean, the more people that we can get to see up close and personal this rocket, it's awe-inspiring. And I cannot wait till the launch. When America sees our rocket actually launch on a test flight to the moon, you know, it's just going to spark a whole new push for what we are doing.
Best day of my whole life ever. It's gonna be incredible. It was a dream come true.
This rocket is definitely going to the moon.
I think it's really amazing.
I was actually really excited because I've never seen a rocket like this close up.
Now we have the Artemis generation. This is a new generation of us going back to the moon to learn and live, and then we're going to Mars.
And liftoff of Artemis 1.
I'm Christina Cook. I'm a mission specialist.
I'm Jeremy Hansen. I'm a mission specialist.
I'm Victor Glover. I'm the pilot.
I'm Reed Wiseman. I'm the commander for the Artemis II mission to the moon.
To the moon.
To the moon.
To the moon.
When I was young, I had a poster of the Earthrise picture, the famous picture that was taken on Apollo 8. And the fact that it was a human behind the lens that made that picture so profound and changed how we all thought of our own home was so amazing to me. The moon is not just a symbol of thinking about our place in the universe. It's not just a symbol of exploration. It's actually a beacon for science. It's a beacon for understanding where we came from.
You know, pushing ourselves to explore is just core to who we are. It's a part of being a human. That's our nature. We go out there and we explore to learn about where we are, why we are, understanding the big questions about our place in the universe. The exploration we're doing is the first few steps on the path of getting humans to Mars.
The Artemis campaign of missions have set such an ambitious goal for humanity that it's inspiring contributions from around the globe. Not just one nation is inspired and moved by this, but nations from around the globe are coming together. When I look at the Artemis II crew with Victor, Christina, and Jeremy, they want to go do this mission. They are keenly driven. They are humble to a fault. It is so cool to be around them. Artemis II is a huge mission, but I hope we will look back and realize that this was one tiny step in humans on Mars and a sustained presence on our moon. Before stage start. Artemis II will be NASA's first crewed flight test of the Space Launch System rocket and Orion spacecraft around the moon.
To verify today's capabilities for humans to explore deep space
and pave the way for NASA's long-term human and scientific presence on the lunar surface.
We are ready.
We are going to the moon for all of humanity. We are Artemis.
You are watching NASA's Lunabotics 2025 finals being held here at the Kennedy Space Center Visitor Complex here in Central Florida. And as we watch the Virginia team come into the arena, they're going to spend the next 10 minutes, maybe more, depending on when the timer starts. They're going to get a 10-minute timer to set up the robot, and obviously that timer hasn't started yet, so we're still getting stuff situated, getting all of our judges ready for the next event after our lunch break. You may remember before our lunch break, we had a really good run from Michigan Tech. And so I have grabbed one of the Michigan Tech students to ask a few questions of. So first, tell us your name, and make sure your mic is really close to your mouth.
Sure. So I'm Braden Moore. I'm the software lead for the Astro Huskies for Michigan Tech.
Software lead. If I remember correctly, you were one of the students that was in the control room during the run.
Correct. Yeah, I was the main mobility.
The one driving the robot.
Correct.
Awesome. That was going to be my my next question. Actually, my next question was going to be, what year are you in school?
We actually just graduated here a couple weeks ago.
Okay.
So, previously a senior, now alumni of Michigan Tech.
Alumni. So, got any jobs lined up? Are you taking a break before you go into the workforce, or?
No, we got a job lined up down in up in Detroit, Michigan.
Yeah.
So close to home.
Excellent. Congratulations.
Thank you.
So, software lead and driver.
Mm-hmm.
So, software lead and driver.
Correct.
What do you, as a software lead, what do you want to tell us about the autonomy software, which we did notice on the, we were watching you guys in the control room to see if you were stick driving or not.
Yeah.
So what do you want to tell us about either generically the autonomy that is that is designed, and maybe a little bit about what happened to the autonomy, good or bad, in your actual run earlier?
Yeah. So we had attempted both traversal as well as excavation deposition autonomy. Traversal kind of went not quite as far as we had hoped it would, so we had to kill it just so we didn't damage the rover. For excavation deposition, it went very beautifully for one cycle. We were hoping for a few more, but we had a couple other errors in the program. So all things we've taken note of, prepared for the next time we give it a try.
Excellent. So you're confident that what you noticed can be fixed, and it's probably being fixed right now behind us in the pits.
That'd be something I work on, yeah.
You're hopeful that, well, let me ask, are you pleased with the outcome of that run? To me, I mean, the uninformed, it looked like a nice sized pile of regolith in the scoring zone. What are your thoughts? Are you pleased with it? You think you can do better? You know you can do better?
I know we can do better.
Yeah.
I've seen that rover be quite capable, especially of mobility. That excavation system is bulletproof. Finally today we found that perfect rock jammed in that last excavation trench.
That's why it ran backwards.
That it did.
I was confused. I was like, why in the world would that thing run backwards?
Yeah. There were a couple instances we noticed it hit something and jammed up, so we'd run it backwards briefly to try to free up that chain to try to get it running again. So we're pleased with the operation. All the systems were working nearly flawlessly. So we're just trying to perfect all of it and get it to all really line up for an even better run next time.
So this is a highly technical question, and this is your final question. What did you see in the control room that told you that a rock had jammed up? Was it just purely a camera stream, or was it spikes on a motor current, or both?
Yeah, it really is both of them. One of them we have a camera that's looking directly down at the excavation, kind of off at a front angle, looking at both the front wheels as well as that excavation bucket ladder. So we can see when that stalls, when it halts briefly. We can stop giving it power, wait for it to, something to settle, run it backwards briefly if need be. But we also are recording a lot of the data from our driver station, and so we can see afterwards as well, especially specifically what happened.
Excellent. Well, I won't keep you any longer. I know the rest of your team is back there working feverishly on the robot. But let's tease the viewers at home about when your next run, when your second run is going to be. So that's going to be tomorrow afternoon, correct?
Correct.
You'll do your second run, which means there's plenty of time between now and then to do some, I wouldn't say major repairs. Figure out what's going on with that rock. Get that rock out of there.
Yep.
I noticed they had to take the thing apart to get that rock out of there.
They did. It took some effort.
So put the thing back together. Put the thing back together.
Yep.
And fix anything else, and tweak anything else that you noticed, and have a good run. So, good luck on your second run, and don't panic between now and then. Just focus on fixing the problems, and good luck to you. Thanks for chatting with us.
I love it. Thank you, Kurt.
So we should be seeing University of Virginia robots in the arena, and they are running. The robot is running. How far are we into our 30-minute timer? There it is. There we've got the timer on the screen. We've just started this 30-minute run for Virginia, and their robot is almost through the obstacle zone. And as soon as it crosses that line that it's touching, it will be in the excavation zone and will be allowed to start digging in that area if it chooses. This Virginia robot has a four-wheel drive system similar to the Michigan Tech robot we saw earlier. I do not believe it has four-wheel steering. I believe this is a skid steer robot, meaning the two wheels on the right and the two wheels on the left are basically tied together. The two wheels on the right are tied together, so they either both go forward or they both go backwards, and the same for the two wheels on the left. They either both go forwards together or they both go backwards together, and this allows the robot to turn by setting one side of the wheels in the forward direction and one side of the wheels in the reverse direction, as you're seeing on the screen right there. We call that, in the industry, we call that skid steer. All right, so the Virginia team has positioned their robot in the excavation zone just outside the deposit zone. And you can see in this view, they're driving away from the camera while their center-mounted, a very large center-mounted bucket drum spins, and you can see every half of rotation a little opening, and that little opening is basically the teeth or the mouth or the jaw of this. And you can see the trench that they left behind. It actually gets deeper as the robot gets further away from the camera. So it's actually plunging this large bucket drum down deeper into the ground as it drives. Here's a reverse angle. You can see the trench that it's making. You can see how deep the treads are on these wheels. So I'll be really surprised if this robot ends up slipping its wheels and losing traction with such deep treads. But everything's a trade-off in robot design like this. With a skid steer robot, sometimes the treads get in the way while you're turning. So we can watch that the next time this robot turns. If it ever decides to turn again, it's possible that this team never needs to turn the, ooh, we're slipping a little bit there. You can see the bucket drum hit something hard, I think, and stopped, and then the wheels started slipping. But they've recovered. They lifted up their bucket drum and relieved that pressure. The bucket drum has clear sidewalls, so you can actually see the Regulus simulant poking through there. Now they're going to come into the scoring zone, and I suspect they'll just spin their bucket drum reverse in order to dump out that material. And we should be able to see it come out this side. There it is. There's a lot in there. And this is just 4 minutes in, 3.5 actually. I love the clear bucket drum though, because we can really see what's going on inside there. All right, that was one run. Now, if we just check on the students real quick in the control room, we'll be able to see whether they're stick driving this robot or whether they're using autonomy. So these are the University of Virginia students controlling the robot in our Mission Control Center. You can see the student on the bottom of the screen is actually controlling a joystick. That's the controller for our pan, tilt, zoom camera. So they have chosen to use one of our pan, tilt, zoom supplied cameras. And then the other two students, looks like they both are driving joysticks. So one of them is likely driving the robot's chassis around, and then the other student is likely, no, I thought that was a joystick. It looks like it's not. So this the second student appears to, I'm sorry, that is the, I'm getting my hands confused. The third student, second from the top of the screen, appears to be holding the joystick and driving every part of this robot right now. So the second digging cycle for this robot, you can see the students chose a different path so that they wouldn't dig in the same spot. They basically took multiple passes at that first path, and it looks like they're taking multiple passes at this path. From this angle, you can kind of sort of see the pile that they had deposited earlier. From this angle, it does almost look like it's not all inside the scoring zone. As this bucket drum comes around, you can see it looks like smoke on the screen, but it's not. It's dust. This fine powder that actually makes up our lunar Regulus simulant is such a fine powder. Think of it like talcum powder. Think of it like baking flour. It's the particles are so tiny that they can become airborne pretty easily. And so that's what you saw, which looked like smoke coming out of the bucket drum, was actually dust from our Regulus simulant. Their bucket drum was so full when we saw that dust was coming out. Now this is something that you hate to see. If you have a four-wheel drive robot, you hate to see one of the wheels not spinning when it's supposed to be. When this robot turns or when this robot drives forward, I suspect that all 4 of these wheels are being commanded to turn, and if you see one of them not turning, that's usually an indication of a problem. Ooh, there's a lot coming out. They're definitely in the scoring zone now. It's very obvious. And that's quite a bit of material. So this is going to give this Virginia team a good score. We're not even 10 minutes into this run, and look at how much material they've deposited into the scoring zone. The students do appear to be driving the robot with a joystick, so they're apparently in their first run, apparently not going for autonomy points right now. But that's not to say that they won't try it later tomorrow afternoon in their second run. I looked up the University of Virginia the other day on the internet, and I found out that Thomas Jefferson actually founded the University of Virginia way back in 1819. Very cool. Did not know that. Alrighty, this pass was just a few inches, maybe 6 inches to the right of their previous pass. Which means they're going to get some fresh soil that wasn't already dug in earlier. A mix of fresh soil and earlier dug soil, which is probably what they were going for. Don't forget, though, as easy as this looks, what you've seen so far from Virginia is them only scraping off the top couple of inches, I would guess. So what you might remember from earlier is that the first couple inches of this simulated lunar regolith is very light and very fluffy. So once they get, you can see it, their drum is full. It can't hold anymore. It's just falling out the top. Once they get past this top couple of inches of light fluffy stuff, it's going to be interesting later on in this run to see if their digging system is still able to dig as efficiently, as productively as it appears to be digging right now. It's definitely going to take more traction, more power in order to dig the later, deeper layers down further than a couple inches below the surface. So far, a very impressive run. This is one of the beauties of a cylindrical bucket drum that digs. In order to dig, you rotate in one direction. In order to offload, you rotate the same exact motor in the opposite direction. So that's a lower number of actuators than some other robots that have more complicated mechanisms that need to transfer the excavated material from one part of the robot to another. This is a design trade-off that all teams have at the beginning of the year when they sign up for this competition, is what type of mobility system do we want to choose? How many wheels? Maybe we do tracks instead of wheels. How do we want to dig? Do we want to a simpler system that's less likely to break down on us, but maybe is not as efficient as a more complex system. If you choose the more complex system, you might have higher productivity up until the point where something fails in that complexity, and then your productivity goes way down. So this is this makes for a really interesting competition every year to see all the different design choices that all these different teams come up with. And behind the scenes, what viewers are not going to be able to see is that each of these teams submit for judging reports that detail their entire design lifecycle process, and it will their reports will detail these design choices that each of these teams have made and explain why they chose them. And so the judges are able to see all the decisions that all of these teams made during this past school year to come up with the final robots that you're able to enjoy on the screen. So much time remaining. We're only halfway through this 30-minute run for University of Virginia. They just went back to an earlier spot. Looks like they're lining up for a dump farther towards the left. So you'll notice they're not dumping in the exact same spot every time. They're trying to spread it out. They're also not digging in the exact same spot every single time. If they spread out their digging, that will decrease the chances of creating a hole or a pit that can cause their mobility system, their drive wheels and chassis issues. It's pretty obvious when this team has filled up their bucket drum, because the material just pours out as it comes around the top. See, watch how much material pours out the top here as they drive forward. No, not that much. You can see from the side view through that plexiglass window that the drum is, I don't know, I want to call it almost half full, but that's just how much of the window is being covered. It really can't hold much more than that. When that drum is half full physically of actual material, it's probably design-wise full. Because as that drum spins, the front side of it picks up material. So if material is halfway in there, it's going to be picking that up as it spins and throwing it out the other side. So at some point, trying to put any more material inside there just doesn't work out too well. I bet if we look at the side view right now, we're going to see how buried those wheels are. These piles are pretty impressively high in the scoring zone, from what I can tell. Yeah, from the side view, you can see the tracks that were left behind. With 11 minutes remaining, University of Virginia is creating really good-sized piles in the scoring zone. I suspect that in their last 10 minutes of this run, they'll probably start dumping over in that far left side of the scoring zone. to spread out their scoring material appropriately. I did notice it kind of got hung up a few times. I wonder, I kind of think that maybe they're in the harder stuff by now. And so it's possible that this team is going to have to be less aggressive now that they're a little bit deeper and they've hit the part of the regular simulant that's quite a bit harder. Ooh. Now there is a rock there that I don't believe this robot would be comfortable driving over, so they're definitely staying to the right of that rock, which is limiting their possible excavation zone, their excavation area. They're kind of only using about half of the total possible excavation area, and that's due to a pretty good sized rock on the far right of the screen and a medium-sized rock on the kind of in the middle of the screen, but to the left of the robot. This one's going pretty deep. I'm impressed. They are getting bound up every once in a while and having to relieve the pressure pushing down on that drum. You can see the digging path that's left behind. It's a nice smooth digging path, and you can kind of see it has an edge. It might be an inch deep or so. So they're definitely into the hard stuff, for sure. Yep, they're going on the far side of the deposit zone now. A clean deposit site. Yeah, from the side view you can see how tall those prior deposits are. They're more than halfway up the wheel diameter. Students in the control room are calm and cool. Just going through the motions, repeating this pattern, finding a spot to dig, slightly offset from the prior spot. They are aware of that rock. There's no question that they know about that rock. They have a similar camera view to ours that they have chosen to watch in the control room. Okay, so now they've turned their robot. Oh, I was wondering if they were going to dig sideways, but no, they were just transitioning to a different track, so they didn't drive over the same track again. Just under 7 minutes for University of Virginia's first run. Anytime you see a smooth excavation path like that, you know things are working well. I don't know if they have a control system monitoring the height and making sure that it stays a certain depth, or if they're students controlling the robot from a joystick are just really good about controlling the height of the dig as they go. All right, going back for some more digging. You can see in this view are the only folks that are in the arena during a run are our judges, and so these three people you see in this shot are all judges. These are not students. You can even see the judges' score sheet there on a clipboard. Under 5 minutes for Virginia in their first run. First run of 2 for all of these teams today. I think they may be full, but there's still plenty of time to go back for more after they dump this load. Here comes Virginia emptying their robot one more time. You can see some of the sensors on this robot in this overhead view. Got some cameras there. Okay, now they're picking a new spot, a brand new spot. They're going to the left of that rock. 3 minutes remaining. So this is actually very realistic for a lunar excavation robot. You're basically going to find an area that you won't necessarily find an area easily that has 0 rocks, but if you can find an area that has a minimal amount of rocks or a minimal amount of large rocks anyways, then make sure your robot can, have cameras, sensors, whatever is necessary to recognize those obstacles that you don't want to try and drive over or dig through, and just avoid them. Nothing wrong with that. This is actually very realistic to one possible future lunar excavation mission. Some teams are going to try and move these rocks out of their way to clear a path, and that's another possible solution that NASA might send to the moon. Which solution ends up scoring better in this competition might actually shed some light on which is the better option to actually send to the moon. So that brings up a good point that one of the benefits to NASA of putting on this competition every year is we get a lot of different prototype lunar construction robots, excavation and construction robots every year, and we can see what works and what doesn't work, and we can take note of things that work and maybe take that back to the lab and maybe implement something similar. We can also maybe see something that doesn't work here and maybe take that back to the lab and maybe try to tweak it or improve it, or figure out what made it not work, and maybe come up with something unique that otherwise would have been just a throwaway idea. Okay, it looks like they're not going to try for another one. They only have 15 seconds left. So let's give University of Virginia a big hand for this big pile of lunar simulant that they've created. Good job, University of Virginia. They should be happy with that. All right, my notes say that University of Alabama is next. Hopefully that's correct. May take a few minutes before that run starts. There's lots of reset process that has to happen, not to mention getting the official scores, getting the laser scan of the Virginia run that just finished up. And so you definitely don't want to go anywhere. You want to watch University of Alabama run next. So maybe take a quick break and come back. Looks like we still have about 100 people watching the live stream. Let's see if we can get that number up. So if you haven't already advertised on your favorite social media account, link to our live stream, or at least a link to our Lunabotics webpage, which has a link to the live stream. You can publish the URL go.nasa.gov/Lunabotics and tell them that you're here competing or you're here watching and you want them to watch along with you. That would really be amazing. So we're going to just watch this team from Virginia as they pull the robot out of the bin, and we'll keep an eye open for the University of Alabama team to get their robot ready for their event coming up next. So don't go anywhere. Continue to watch right here NASA's 2025 Lunabotics competition, streaming live from NASA's Kennedy Space Center here in sunny Central Florida. Don't go anywhere.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
Go. Prop. Go. PD8. Go. Fido. Go. All right. Go for launch.
Our destiny is always to go and see what's further and what's next.
Fido. I'm running the launch.
What an exciting day at the Kennedy Space Center. You can see the Orion spaceship coming out of the ONC building where we've been assembling it for several years. As big a step as this is for us today in rolling out and starting the journey of Artemis 1 to the moon and beyond, we're really excited for this test program to get this vehicle flowing and to begin the next steps, which are to send humans back to the moon.
The twin sister of Apollo, Artemis is the name given to the program that will return humanity to the moon. And named after one of the largest constellations in the sky, Orion is the spacecraft destined to get us there. Through Artemis missions, NASA will land the first woman and the first person of color on the lunar surface. And these missions will allow us to explore more of the moon than ever before, paving the way for long-term presence in lunar orbit.
We're rolling the Orion spacecraft out, but it's beginning its journey. We're really kind of at the end of the building process and the beginning of getting ready to go fly.
But before Orion can travel to our nearest celestial body, it must first make a few pit stops along the way to fuel up and get ready for flight.
As we leave here today, we're going to go to a facility that'll fuel the spacecraft with the rocket fuels and propellants it needs. We'll put a launch abort system on. We'll send it out to be stacked in the rocket and launched. And it's really the last few yards of the game.
Orion's journey to the moon began on the bayou. NASA's Nishu Assembly Facility in New Orleans is where technicians with Lockheed Martin began welding the pieces of the spacecraft's underlying aluminum structure together. 1 year later, it arrived in Florida, taking up semi-permanent residence inside the Neil Armstrong Operations and Checkout Building at NASA's Kennedy Space Center. Engineers and technicians will spend the next years working almost around the clock, outfitting Orion with thousands of components and pushing the capsule through several rounds of rigorous testing as teams prepare for its flight around the moon. The first step, though, is the crew module's arrival.
When the crew module shows up here at the O&C building, it's really just a welded shell of the structure. When it gets here, we put it into a fixture called the bird cage tool, and we use that fixture to position and attach all of the mechanically attached primary and secondary structure for the crew module.
Part of that includes the heat shield, which protects the crew module as it blazes through Earth's atmosphere at astonishing speed as it returns home. Technicians with Lockheed bond those thermal protection system products onto the heat shield right here in the O&C. And they do the same for the crew module's forward bay cover.
We bond that on here, and basically this covers the forward bay of the crew module such that once we come back into the atmosphere, this gets jettisoned and all of the landing system, i.e. parachutes, get deployed and slow the crew module down so that when it touches down in the ocean, it's only going a few miles an hour.
With the primary and secondary structures all attached, the crew module is tested to see how everything holds up. Orion is pressurized, stressing the welds to ensure they'll hold up under the proper loading. Afterwards, non-destructive evaluation of those welds is conducted to check for any voids or cracks. Once the structure is deemed strong enough, the crew module is moved just a few spaces down into the O&C's clean room for its next round of integrations.
We bring that structure into our clean room, which is you see behind me, because we need to start integrating the propulsion system and elements of the environmental control and life support subsystems, and those systems require a cleaner environment than the one we're standing in out here.
When all of that is done, the crew module is on the move again to the crew module integration station. There, all of the electrical systems, including wire harnesses and avionics boxes that control the crew module's guidance, navigation, communications, and its power subsystems, are integrated. Next, it's time to bring the spacecraft to life.
We power it up, and then we go into a whole series of functional tests to make sure all the subsystems that we've integrated up to that point are functioning properly.
But the crew module isn't the only thing that makes up the Orion spacecraft.
All the people, the work, the components that have gone into this vehicle, it's just an amazing feat.
Teams also worked closely with the European Space Agency to build the service module, the element that will power Orion on its journey around the moon. Once that arrives from Bremen, Germany, Lockheed moves forward with integrating the two.
The service module has a very similar life cycle to the crew module. We build it up structurally, we integrate the propulsion system and the other fluid systems, and then we integrate it electrically and power it up and do functional tests on it. And when we have a full service module and a full crew module, then we stack the two together and we have what's called the crew service module for Artemis 1.
Under the Artemis program, NASA plans to not only return to the moon, but to use that as a stepping stone to go farther than any human has ever gone before, Mars. To get there, it's truly a cross-country and international effort among thousands of individuals.
When you consider all the people, at the Johnson Space Center, Marshall Space Flight Center, all across the agency, SLS, Orion, the European Service Module, Boeing and their team, Lockheed Martin and their team, and to see all of that come together on that launch when we send it on its way to the moon, it's going to be absolutely amazing, and we're going to have a lot of really proud, happy people.
Building a spacecraft destined for deep space exploration from the ground up is no easy task. And the fact that these teams have been able to come together and do just that in the midst of a global pandemic is nothing short of amazing.
It really is a testament to the workforce. If you think about what we've been through over the years that they've been putting this together, and particularly think about the environment that this team was dealing with. We're dealing with COVID, and we're asking these folks to come into work every day and finish the spacecraft so we can keep this mission going. And we're ready, and we're excited. And so as they turn this over to us, we're ready to get going.
And really, this is only the start of Orion's path to the pad.
It's a little hard to put into words when you think about the fact that we are in the first flow of what will be our nation's deep space exploration program. It hits you in the heart, and it really speaks to why we all are doing what we're doing.
I never thought as a little kid growing up I'd be part of something like this today. Now as a dad of two young girls, to be able to tell them what I do and to be able to have them someday watch the first woman stand on the moon is pretty amazing to me personally.
As the Orion spacecraft departs the ONC, its next stop is the Multi-Payload Processing Facility, or MPPF, where teams with NASA's Exploration Ground Systems and prime contractor Jacobs will perform the next set of milestones, fueling and servicing the spacecraft.
We have a few months of hard but rewarding work ahead of us to get to launch, but this is it. This is our year.
You're watching the Lunabotics finals event from 2025. On the screen, we are looking at the laser scan from the University of Virginia run. You can see very clearly the 3 piles that their robot has deposited. And this laser technology allows us to scan the surface before the run and after the run, and then perform some simple math, simple matrix math, right? To calculate the volume between the 2 scans. And that's pretty fun to look at the data in 3D. 3 obvious, pretty decent sized piles there. And in the arena, the judges are resetting the surface and getting ready for the next team, which is going to be the University of Alabama. They will be coming into the arena soon. Matter of fact, the Alabama students and their robot are in the room right next to the arena, but the judges are not quite ready yet for them to bring the robot into the arena. So we will be looking forward to that in the next few minutes. So don't go anywhere, because you don't want to miss Alabama. They tend to have a strong showing in this competition. But honestly, we're down to the final 10 teams, right? The best 10 teams. So we expect strong showings from all 10 of these teams. witnessing here today, tomorrow, and Thursday. I did mention this earlier, but it's probably worth repeating that Lunabotics spans an entire school year for these teams. And it requires these students to apply NASA's systems engineering process in order to design, develop, build, and test their prototype lunar robots. Throughout the year, the school year, these student teams have to prove to our judging staff that they are progressing throughout the school year. And so all of these student teams have previously submitted STEM engagement reports to show our judging staff how they have engaged and interacted and educated students about their robot. They have submitted presentation and demonstration slides. They've submitted systems engineering papers and proof of life videos. All of this work, all of these submitted deliverables before ever being allowed to compete here with their robots. I mentioned a couple times that the Lunabotics competition, the actual process, requires these college and university students to actually apply NASA's systems engineering process. But I haven't really explained what that means. Systems engineering, if you're not familiar, focuses on designing and building and managing complex systems. And since rockets are complex systems, spacecraft, satellites, interplanetary robots, these are all pretty complex systems. Turns out that NASA has become pretty proficient at using a systems engineering process. And so that is why we're teaching these students the systems engineering process. What you're seeing on the screen is our arena, our simulated regolith arena that is full of tons and tons and tons of simulated lunar soil. There's a scientific word we use when we refer to lunar soil. We usually call it regolith in the space industry. It's a kind of a fancy word, but it really just means soil on another planetary body, and that's any place other than Earth. So the moon has regolith, Mars has regolith, but you can really just think of it as moon dirt or Mars dirt. On Earth, we only have a small amount of actual regolith that was returned from the moon back in the 70s during the Apollo program. And we don't have any samples on Earth of Mars regolith. Not yet, anyways. And so what we're testing these robots in is a bed of simulated lunar regolith rather than using the real thing. But if I slip and call it regolith this week, forgive me. But it is obviously simulated lunar regolith. I mentioned earlier that our simulated lunar regolith is volcanic rock that's been crushed to a fine powder. And it turns out that's actually a pretty decent stand-in for lunar soil. I've mentioned a couple of times different trade-offs that these student teams have to make when designing their robots. all of these student team solutions vary from one another. Each team tries to think outside the box and come up with new ways to solve the problem of digging lunar soil and then constructing berm structures or hills out of that excavated material. And these student teams each year perform full-blown system designs complete with engineering trade-offs. They don't just throw a bunch of stuff together and hope for the best. And the rules of this competition really, truly encourage the teams to perform these engineering design trade-offs. And so this competition really does teach these students about real-life engineering processes, because engineering in real life is actually a mix of following a strict logical process combined with creativity and out-of-the-box thinking and trying crazy ideas, and that's what these students end up doing each year in order to compete in this event. One example of an engineering trade-off that all teams have to perform for this competition is a size trade. The rules do require that each team solution has to fit inside a box, a literal box that's 1.5 meters by 3/4 meter by 3/4 meter. That's roughly 5 feet by 2.5 feet by 2.5 feet. And that physical size of all of these robots is a hard limit. So the various solutions that each team comes up with has to somehow fit within that physical size. If not, then that idea just has to be abandoned. Another example of a trade that these students have to perform is the weight of their solution. The Lunabotics rules state that the weight of these robots has to be 80 kilograms or less. That's about 175 pounds. So any ideas or solutions that a team comes up with has to end up weighing 80 kilograms or less. If not, they won't be allowed to compete. So looking at just these two rules, the size limit and the weight limit, those two rules work together and they limit the onboard power of these solutions. It makes sense that batteries tend to be heavy in general. So teams have to trade off how much of their total 80 kilogram total mass that they're going to allow for batteries so that they reserve enough mass for the rest of their robot. Another big design trade-offs for teams is that they all have the option of making their solution actually quite a bit lighter than the 80 kilogram maximum weight if they want. And so a team might do this on purpose because the largest portion of their score, which actually a full 50% of their score, is based on how big of a berm they create divided by the mass of their robot, plus how big of a berm they create divided by the power used by the robot. So in other words, a majority of the score isn't just based on the size of the berm they create, but it's based on the size of the berm they create as compared to their robot's size and power. So that means a smaller, lighter robot that uses less power but is still capable of creating a reasonably sized berm could potentially score very well. That's why you might notice that some of the Lunabotics finalist robots are bigger and some are smaller. On the screen now, you can see the Alabama team. They've put their robot into the starting position in the bin, and they are right now attaching a visual marker that the robot will then look at later on in their run in order to determine where it is in relation to the starting position. An obvious indication that this team plans to run autonomously, at least for some of their run. And now that we see the timer on the screen, they have 8.5 minutes remaining in their 10-minute setup time. Looking ahead on the schedule, after Alabama's run, we will get to see Milwaukee School of Engineering perform their first run of Lunabotics finals. In the control room, we can see Alabama students setting up their computers to monitor the data from their robot and send commands to their robot. We will possibly be able to watch these students during the run and see whether they're driving the robot or whether it's performing autonomously. Speaking of autonomous robots, one of the other design decisions used to be a big trade-off for teams, but now pretty much all teams do it, is autonomy. And autonomy means letting the robot think for itself and control itself. Autonomy does require additional sensors, additional communications, additional power, and it's not exactly trivial to make it work. So that being said, the reason most teams do autonomy in this challenge is because we have purposely made autonomy worth a lot. We've made it a full 30% of their final score. So we, the designers of this competition, are actively and strongly encouraging teams to create autonomous robots rather than manually stick driving them during this competition. You can see the Alabama students have moved their visual navigation target into the corner of our arena, which I suspect gives the robot a pretty clear view of it, no matter where that robot moves to inside the arena. All right, less than 5 minutes remaining in Alabama's setup time. You can see students talking on a radio, possibly talking to the students that are in the control room to verify that everything is operating, communications are working. Students are encouraged during this 10-minute setup time to make sure all the data is working, all the commands are working without really moving the robot very much. Kind of a wiggle test. And to verify that they're ready for their competition to start before they leave the arena. So we'll know that these students are happy with their robot when we see them step out of the arena. Which is what they're doing right now. In order for a robot to perform its mission autonomously, it's going to need some sensors that will give the robot the data it needs. A pretty common sensor for autonomy, and also pretty inexpensive, is a simple camera, a simple visual camera. But there are sensors that give you more data than just a 2D visual camera view. There are 3D cameras or depth cameras that you'll often see on robots that compete in this challenge. You'll also see laser scanners, which I suspect is that cylinder-shaped object on top of the robot, at the tip of the blue arrow on top of the robot. That's very likely a scanning LiDAR sensor, laser sensor that can basically take a 3D picture of the environment around the robot for the onboard camera to make decisions on. The onboard camera can take that 3D laser scan and decide, there's a pretty tall thing right there, I should probably avoid that, that's probably a rock. Or there's a pretty deep hole there, I should probably avoid that, that's probably a crater. But another thing that autonomous robots often use are 2D images of specific patterns, like the pattern shown on camera 2. This pattern, which looks kind of random to our human eyes and brains, is actually a very specific pattern that a robot can use, and it can calculate with precision by looking at this image. It can calculate with high precision where the robot is in 3D space in relation to that pattern. It's kind of like a special barcode for robots. Instead of the barcode telling the robot a URL for a fun website, like what we humans often use barcodes for, these barcodes basically tell the robot where it is in 3D space, which is kind of cool technology and doesn't require expensive laser sensors. It just uses simple old school 2D image cameras. Here we see the students. Their setup time is almost over, and now we have started the 30-minute event timer. So usually for an autonomous robot, it's obvious the students are not touching keyboards or mice or joysticks. They even backed their chairs up to make it even more obvious that they were hands off. But if we cut to the robot, we can see it hasn't moved yet, and this is not uncommon for an autonomous robot. Most autonomous robots need to spend a few minutes scanning the terrain and making decisions, making maps, and then planning paths, safe paths through the map that it just created. So this is probably what's going on right now. And there the robot is moving. So its first order of business is going to be leaving the starting area in the direction of the obstacle area. Which is essentially the direction it's driving right now. So there's already an obstacle, a rock on the left, a crater on the right that this robot has already avoided. But there's more rocks down below that this robot should be looking at right now and deciding to avoid, hopefully. Now I notice the students are not looking at cameras that we're providing, but they are looking at data on their laptops. So I'm sure they're seeing live camera views, which show that the robot did try and drive over that rock, but students are holding back, taking over control, because they know if this robot can get past this on its own, they will get a much better score than if they decide to take over manual control. So this robot can probably drive over this rock, even though it's a decent-sized rock. Oh, from this angle, it's actually better from this angle. We can see that it's actually up on top of the rock. Just needs to continue driving to get to the other side of this rock. But I wonder if it noticed, if it sensed the roll, the fact that the robot is no longer level, and maybe decided to stop and think. So the students have still not touched their keyboards, but as time gets short, they're going to have to make a decision. Do we call it? And just take over manual control for the sake of time? Or do we let autonomy continue for the sake of points? So not only did these students have to make tough decisions all year long in designing these robots and building these robots, even the actual final runs, they're still having to make pretty tough real-time decisions. They're so we have multiple judges that are sitting right next to the students in the mission control room, and those judges are communicating with the students to be very clear about whether they are in autonomy or whether they are taking over manual control. Sometimes it's obvious just based on the speed of the robot. More often than not, if a robot is driving slowly and carefully, then it is in autonomy. And more often than not, if a robot is driving fast and a little bit reckless is kind of a rude word, but that's kind of what it looks like. Having a little more risk to their driving. Most of the time, not always. That's a student, purposely being aggressive with their driving. Autonomous software is very rarely designed and written to be aggressive. But it's not to say that you couldn't do that. With a good enough computer and good enough sensors, and good enough software, your autonomous software could be very aggressive. So we're 6 minutes into this run for the Alabama team. And they're still autonomous. The students are not touching their keyboards. And the robot has made it past the obstacle area, went through the digging area, and is now sitting in the deposit area or the scoring zone. It's possible it's doing a scan now of the digging area that is in front of it for the purposes of deciding exactly where to dig and where not to dig, and what patterns to dig in, what patterns not to dig in. So it's possible that once that's figured out, that this robot is just going to go gangbusters and just go crazy in the digging zone and just completely make up for what at first glance might appear to the layperson as some wasted time. All right, here we go. I think the robot has mapped its digging area. It's turned on its digger. It's rotating it down into the surface. Looks like a pretty good spot to me. And now goes pretty deep. Deep enough that it got past the light fluffy stuff, right? And it got into the tough stuff. That's what caused all that rocking back and forth. There's a lot of resistance there. Now this robot's driving forward as it digs. It's a four-wheel drive skid steer robot with a rotating bucket ladder and a conveyor belt in the middle of the robot. If you look at the back of the robot right now, you can see the conveyor belt is actually dropping just a little bit of material out the back. Not in the scoring zone, but this is just probably some residue. I think probably the brunt of the material on board we can't see. It's covered up by all the electronics in this robot. Speaking of covers, one of the design features of all of these robots is the ability to excavate, like you're seeing here, without kicking up a lot of dust. And robots that can excavate without kicking up dust will get a scoring advantage, a slight scoring advantage anyway. There's actually a score for dust covers and the design of a dust minimization system that is scored by our safety judge. And then actually in the arena, when each team runs, they get another score based on how much dust or how little dust, I guess, they actually lofted during their digging. You can see the digging hole they left behind, the digging trench actually, and now we're going to see them dump. You can see a door open up on the back of the robot. It was trying to keep all that material in while the conveyor was rotating, and we can see a good amount of material, and they're only about halfway done dumping right now. You've got a pretty nice pile already. So that was just the last 2 minutes of what we just watched was a full cycle of digging and dumping. So you can do the math. If they do that, what you just saw 10 more times before their run is over, they're going to have a lot of material in the scoring zone. So this is interesting. The robot is basically starting in roughly the same place as it did before. I don't know if this means it's going deeper. going over the same digging spot, but plunging their digger down so that it makes a deeper hole, possibly. You see how much shaking happens. They're way past the light and fluffy part of this simulated lunar regolith. They're digging in the hardest part of this material, even though it's still particulate material. It's basically dust that's compacted and held together like jagged puzzle pieces. And so it is not easy to dig in at this depth. But this robot appears to have the power it needs. We don't see any spinning wheels. They've got the grip that they need on the wheels to counteract the forces that are being applied to this bucket ladder digging system. So this second run appeared to go in the exact same slot trench that they had dug the first time. It's be interesting to watch what pattern arises from this autonomous digging system. The students still have not touched their computers. In this view, you can see the hole that was left behind. In that side view, we'll be able to see if they dump in the same spot or if they adjust a little bit so that looks like they're dumping in the same spot. I love that the sides of their conveyor are plexiglass, and you can see through them. You can see the material sliding back from that conveyor. All right, so that was 2 cycles of digging and dumping. And their dump pile is basically, the tip of the dump pile is basically the height of that conveyor almost. Almost the diameter of their wheels. That is a really significant sized pile of material. And goodness, they have so much time remaining, 16 minutes remaining. Okay, they go in the same hole again. I'm actually surprised. So they can go deeper. I can tell that their bucket ladder system is deeper than it was before. So they're hitting the same slot trench 3 times, deeper each time. Surely this is as deep as this robot can dig, or can it go even further for the next run, for the next cycle? While they're digging and while their conveyor belt is rotating, which rotates while they're digging, they're losing just a little bit out the back of the robot. But the back of the robot does have a door that's closed, and it has a little bit of a seal there that is letting a little bit through. So they're losing just a little bit of potential points there, but I don't think it's a significant amount. Students continue to just watch their screens and not touch them. They're all perfectly stone face. No reaction. This is the third cycle in that same digging spot and the same dumping spot. Be interesting to see what they do next. Looks like a fourth run on the same spot. This hole is getting super deep. As long as the robot's wheels straddle it and don't fall in, they're going to be in good shape. Again, this is University of Alabama. Their first of 2 official competition runs here in Lunabotics Finals. Looking ahead, we're going to have Milwaukee School of Engineering coming up next. 12 minutes left for Alabama. This run appears to be fully autonomous. They've had several cycles, back and forth and back and forth and back and forth, where the students have not touched their computers. They actually pushed their chairs away from the table. Arms crossed, just watching the robot do its thing. Eleven minutes remain for Alabama's first run. I may have lost track, but I think that was the 4th run in that same exact hole. How deep can this robot actually go? Looking back at the hole on camera 3, you can see it did fill in a little bit. Some of the side walls have fallen down a little bit, which gives them a little bit of free fluffy stuff. Anything that falls in there, it's going to be light and fluffy and not going to be very difficult to dig in. They are straddling, completely driving over the hole they just, the trench that they just dug, which has got to be at least, I don't know, 10 or 12 inches deep. You can see the front left wheel is on the edge of that trench. This is precarious right here. That is a deep trench, and that wheel is, both of these left wheels are going to be very close to the edge of that trench. And I'm not sure the students in the mission control room know that, because they do not have this camera view in front of them. They chose zero. They chose to use none of our 2 possible optional camera views, and so any cameras that they are looking at on their laptops are onboard cameras. So unless they have an onboard camera looking down at the wheels, the students may not know how close this robot is to falling in that deep, deep trench. So if patterns are, you can see the rear wheel, you can see the track that the front wheel made on the left, and then you can see the track that the rear wheel is making. The rear wheel is even further to the right and really at risk of falling into that hole. But what I was saying was, since it took 4 passes at that first trench, maybe it's going to take 4 passes at this one. I am really worried that taking 4 passes in this spot is going to cause this robot to fall in that big trench. The whole left side of the robot looks really, really close to falling in that trench. 7.5 minutes remain, and look at that rear wheel, very close. So the robot has shifted to the right. You can see its old track and its new track. It shifted to the right, which is why these wheels have gotten really close to the edge of that trench. So is the robot cognizant? Is it doing a scan every time, or did it just do a scan at the beginning and is just keeping track internally where the trench is? If the latter is the case, it's possible that the robot has shifted to the right and the robot doesn't realize it. It's also possible, based on what camera views the students are looking at, they may or may not realize the robot is shifting to the right, and they may be right now trying to decide whether they want to take over manual control or continue this automation. If they're lucky, and they have been so far, rather than falling in all at once, it's just going to fall in, just sink in an inch deeper each pass. And if that's what happens, it's not going to be the end of the world for this robot. 6 minutes remaining. It's also quite possible that I'm being overly dramatic, and it's quite possible that if this robot falls into its trench that it is fine and it can just drive on out. Sometimes these robots have more power and more grip than we think. 5 minutes remain for University of Alabama. I mentioned earlier that this crushed volcanic rock, which is used as our lunar soil simulant, our regolith simulant, is fine-sized particles that are jagged in shape, and that's what causes the deeper material below several inches to be kind of tough and hard to dig in. That is actually helping this robot not slip into the trench, because those left, the wheels on, I keep calling it the left side of the robot, but honestly, I don't know. Yeah, that is, according to the arrow on the top of the robot, the left side of the robot is the farther wheels. And so imagine that trench, which is on the right of the robot right now. Imagine that trench. If that was made out of sand and a heavy robot drove on it, it would sink. The sand would fall right in there. But because this material, this crushed volcanic rock, is made up of jagged particles, that wall that the left wheels are driving on right now is holding the robot's weight, and it is not falling in. This is going to be true of lunar regolith on the moon, and it's also true of our simulant. And I believe that property, which makes it harder to dig in this stuff, is actually making it easier for this robot to drive very, very precariously near the edge of this trench without falling in. So in this case, what most NASA engineers consider a downside to lunar regolith is actually kind of saving this robot from falling into its own pit. Under 3 minutes for Alabama's first run, and that pile that they have made is really, really good sized pile. And the students have yet to touch their computers throughout this entire run, as far as I can see. Those arena judges are going to have their work cut out for them after this run, filling in this deep trench created by this Alabama robot. A minute and a half remaining. Now the students, I don't know if the robot is aware of the time remaining or not. I'm not sure that the students have a means of passing that information to the robot, although it could just start an internal 30-minute timer, I guess. Reason I bring it up is if the robot's not aware of the time it has left, it may miss depositing this last load. If it's aware, then hopefully it'll get back and deposit it, even if it wasn't finished. Fully filling up its onboard hopper with less than a minute remaining. Hopefully this team can empty their hopper in the last seconds of this run. No problem at all. I think they timed that just perfectly. Let's just assume that was on purpose, that they used every last second of their 30-minute run in order to maximize their delivery. So in the last few seconds of this run, let's give University of Alabama a big round of applause. Great job, University of Alabama. A great showing for their first run of 2. And as we get the arena reset for the next team is going to be Milwaukee School of Engineering. So we'll continue to watch scenes from various cameras around our event as we get ready for the next team. Milwaukee School of Engineering. After that, we're going to have University of Utah. After that, Colorado School of Mines. And then I suspect we will be done for the day. We will have gotten through 6 teams plus our demo team. And we will run the last 4 teams of our 10 finalists tomorrow morning. which is Purdue. I'm sorry, our last three. Purdue University, University of Illinois Chicago, and University of Akron are planned to run tomorrow morning. I mentioned this earlier, but if you missed it, we will be starting our live stream at 8 o'clock each day. And looking ahead tomorrow, the teams will start getting ready to go in the arena about 8:45. We should start the Purdue run tomorrow morning 9 a.m., 9:15. You might as well just show up at 8 when we start the live stream, just in case things run early tomorrow. So don't go anywhere you don't want to miss the next three robots of the day: Milwaukee School of Engineering, University of Utah, and Colorado School of Mines. You're watching NASA's Lunabotics finals for the year 2024-2025 school year, streaming live from NASA's Kennedy Space Center here in Central Florida. Don't go anywhere. All right. As we watch the Milwaukee School of Engineering students put their robot into the bin and go through their 10-minute initialization steps, we have an opportunity to speak with one of the students from the Alabama team, which just ran. Thanks for joining us. What's your name?
Hi, my name is Tristan Fox.
Again, because we didn't have your
Oh.
your mic hot. Not your fault. Not your fault. Ours.
Okay. Yes, my name is Tristan Fuchs.
Awesome. What year are you in school?
I'm a junior, a rising senior.
Rising senior.
Yeah.
Awesome. What is your role on the team? What do you do?
I am the team lead and also specifically the mechanical lead for Astrobotics.
Team lead and mechanical lead.
Mhm.
Where were you watching that run from?
So I was in the control room.
Okay. We have a view of the students in the control room right here. So we were keeping an eye on you guys, and it looked like you were basically sitting like this the whole time, didn't touch your machines the entire time. Is that the case? Is that what happened?
I mean, you know, we ran it as we touched it as little as we could, you know.
Mm-hmm.
So.
Mm-hmm. It should be noted that if they every time they do touch their computer or their joystick, there are judges sitting right next to them that are taking note of that. So can't sneak anything past our judges. Without revealing any secrets that you don't want the other competitors to know about, can you tell us about that run? What went really well? What maybe didn't go so well? Without revealing any of your secrets?
Yeah. So what went well, obviously, was our mining and construction. We built a crazy berm. We dug a lot. We dug for as long as we could. Once we got to that step. And I'm very happy with our efficiency on that. We've done a lot of tuning this year to make that as efficient as possible. But one thing that went wrong this run is everyone that was watching saw it. We got stuck on a rock as we were turning a corner, and that just really held up our navigation system. So we lost a couple minutes there, but eventually our robot got out of it, and we got to continue with our run.
You know, that happened so long ago, getting stuck on that rock, that I completely forgot about it. And, you know, you collected and deposited so much material that it seemed, from my perspective, it seemed inconsequential. But from your perspective, you know, every second counts. And so you lost, what, I don't know, 15 seconds, 20 seconds in that?
I'd say more like 30 seconds to a minute.
Mm-hmm.
We'll see. Time flows different in that room.
One thing that I noticed, because I have a camera that I can control, pan, tilt, zoom. And what I was noticing was every time your robot came, after you made the initial trench, you did what, 4 passes on it and got deeper each time?
Yep.
Then you drove over that first trench to start your second trench. Did the students in the control room know that when you drove over the deep trench that your left wheels were really precarious and really close to the edge?
We knew that was likely, but our drivetrain, our whole system is designed to be able to take that, and we knew that we could have our wheels fall in there and still probably be able to operate. So it was a risk we were willing to take. I
was getting scared and excited there, but then I thought, you know what? They probably can drive right out of that thing if they fall in. So you just verified my hopes anyway. All right. Thanks a lot for joining us and answering my questions. Have a great rest of the competition, and good luck with your run number 2.
All right. Thank you.
So we're having Milwaukee School of Engineering. You can see the students. You can see their robot moving, doing the little wiggle test. And so they're going to be going, they're going to be running soon as their 10-minute timer, setup timer, which is now at 6 minutes, has completed. So stay tuned. Don't go anywhere. You don't want to miss Milwaukee School of Engineering. Thanks a lot. You can move the chair now. Don't fall backwards, because you don't. That's right. You're watching NASA's 2025 Lunabotics Finals competition, and this is the Milwaukee School of Engineering, as you can see on the screen. They're 2 minutes into their 30-minute run, their first of 2 official competition runs. They've made it through the obstacle zone. They're now in the digging zone, the excavation zone. You can see they're lowering their excavation buckets. You'll notice this robot has 6 wheels. It's a 6-wheel drive robot. I suspect all 6 of those wheels have motors. Yeah, you can actually see them in the shot. It's interesting, though, the steering of this robot, it's the 4 corner wheels that steer. The center wheels stay stationary or non-steering. Now, the digging implements, which were just lowered to the ground on the front and the rear of this robot, are bucket drums that rotate. They're hollow inside to collect the material. You could see in that view the material actually falling in to the bucket drum on the right just then. And this robot isn't designed to go super deep, and so what you'll notice them doing is taking a bite and then rotating or moving to a slightly different spot and then taking another bite. You can see the 4 outside wheels turning in order to spin in place. Oops, some of the wheels were not in the straight position just then when they tried to drive. That is going to make it hard to drive if they don't get those wheels straightened out. This is one of the points of concern. Some of these design trade-offs are more complex than others. When they work, they're really going to pay off, but a complex solution that gives you trouble might be more trouble than it's worth. Hopefully this 6-wheel drive system with 4 steering wheels will pay off for this Milwaukee School of Engineering team. Now, since this robot has digging buckets both on the front and the rear of the robot, they're going to have to dump half of the buckets and then turn around and dump the other half. If we take a quick peek at the students controlling this robot in the control room, we can see that they do not appear to be autonomously operating this robot. They appear to be typing commands into their computer, and they're viewing one of the 2 provided camera views that we provide. So students have the option of viewing 0, 1, or 2 of the camera views that we have available to them. Trade-off being if they choose 1 or 2 camera views, there's a slight point penalty. Ooh. There appears to be a motor or a control issue keeping these wheels pointed in the direction that they need to be pointed. It also appears that some wheels are spinning while some are not, which is causing the robot to have some control issues. You definitely want all of these wheels, and you can see the motors sticking towards the inside of the robot. You can see that each one of these wheels has a motor, but right now, just then, only one of them was moving. And that is never a good situation. You want all of your motors to be moving in this tough material. Otherwise, you're just fighting against yourself. Your robot's fighting against itself, and you're going to get a lot of slip and a lot of either non-movement or movement in a direction you don't want to be moving in. So they got the robot turned around, and now they're dumping the other side of the drums. I noticed that these drums are welded. So the pretty thick material that these drums are made out of in order to be welded. And that gives them the strength probably that they need. Probably aluminum, although I'm not a materials expert. All right, Milwaukee School of Engineering robot going back for its second bite. You notice these arms are being lifted and lowered by what looks like ropes or cables, and they give slack when the arms actually touch the ground. So the arms aren't being driven downward per se. They're being lowered, and gravity is basically the force that's pushing these things down. Doesn't appear to have a motor that's actually pushing these things down, and it's perfectly fine if it's not necessary. Why add a motor to your robot that's not necessary? Or why go to the trouble to create a more complex system when a simple system will do the job? Sometimes as engineers, we tend to over-engineer things, and part of being in a competition like this is having restraint and not adding complexity to a system that doesn't require it. And if you can do that, if you can create the simplest system that can do the job and be competitive, that might be what it takes to win this event. All right, I think they've got 4 full buckets. They're 10 minutes in, so only 1/3 of their time has elapsed. You can see the judges pointing and talking to each other about what they're seeing. These are NASA engineers, these judges. They are working in robotics, ISRU, in situ resource utilization. They are designing, building, and testing robots to excavate lunar regolith, to transport lunar regolith, to construct on the moon using lunar regolith, and so they're all over this technology, and they're excited to see here this week. They're excited to see 10 different prototype lunar excavation and construction robots and be able to learn from all of these different designs. I mentioned earlier, I think it was the Virginia team had a a big bucket bucket drum. These bucket drums are pretty simple devices that are a rotating drum with a mouth, an opening, a jaw that basically digs in. So the drums themselves don't necessarily have moving parts. You just rotate the whole thing as a unit. And if you apply the right pressure in the right direction, you can do you can do the job. Ooh, one of those steering wheels is not steering. It's possible that it was just kind of caught on something and was hitting a maybe overly conservative current limit. So not necessarily the end of the world for this team, especially if they find their problem and fix it and have a really good run. It's possible to have a so-so run and then a really good run in your second run and end up with a pretty good standing. Right now we're looking at another wheel, the corner wheel that is for steering is obviously not steering in the right direction. It's almost turned all the way 180 degrees out because the motor is sticking outside the robot and it's intended to stick in. So that steering motor is doing things that it is probably not supposed to be doing. So that's causing this robot to bind up in its mobility system. Its wheels are just fighting against each other at this point. That is not a fun place to be in for this team. With 16 minutes remaining, though, this team has an opportunity to troubleshoot, maybe even make corrections. They definitely have an opportunity to troubleshoot and make corrections after this run when they get their robot back in the pits, but whether they'll be able to correct this situation and get some more regular simulant into the scoring zone, that is the question right now. Their run is almost halfway through. Oh, they just dumped the material out of the back of their robot, an obvious non-scoring location. Possibly their first step in troubleshooting. Let's look at the students in the control room for a second. Look at their body language. You can see on the left the camera view that they're looking at. This is a house-provided camera. We're providing this camera for them, and they're taking a little bit of a score hit in order to use this camera, but it really gives them a great overhead, a nice overhead view of their wheels and their steering systems that are giving them some trouble. So now that their robot has been emptied, maybe they'll be able to do some troubleshooting and maybe even some correction. That wheel on the right side is so far in the wrong direction that it is also spinning in the wrong direction when they command it. It's actually spinning against the rest of the wheels and digging itself. It's digging itself a little bit deeper. I'm actually impressed that the robot is doing what it's doing right now. It is actually dragging itself through through this tough simulated lunar regolith, lunar soil. Oh, now the other wheel flipped around backwards. Wow. So right now this Milwaukee School of Engineering team has 2 steering wheels that are almost completely facing the wrong direction. Impressed with the power, though, that it can actually drive in this crazy configuration, at least a little bit. Pretty obvious that the team is troubleshooting and looking at the situation and assessing and not necessarily trying to score right now. Okay, that wheel just flipped back. I wonder how they did. Oh, and then the other one flipped out again. It's tough to watch, but if the students are actually learning and troubleshooting, then it's worth it. The robot is tough enough that driving in this crazy configuration in the last few minutes hasn't obviously broken anything. I mean, a wheel didn't fall off or anything crazy like that. You have to remember that these students, one of their trades is creating the lightest robot that they can while also being tough enough to do the job. And so these students, they didn't overdo, they didn't go too far and make their robot too lightweight and too wimpy. It is powering through this regular simulant, even though some of its wheels are just completely sideways and pointing in the completely wrong direction. This is a tough robot. So our hope is that the students are taking this time in the regular simulant to learn. You know, getting a robot running around in this Luna Regulus simulant is not an everyday opportunity for most of these teams. A lot of these teams actually practice on beach sand, which is fine, except that it doesn't behave like Luna Regulus or Luna Regulus simulant. And so any opportunity that a team has to practice and learn in this Regulus simulant is time well spent. So if these Milwaukee School of Engineering students can troubleshoot and learn and bring the robot back to the pit and make some changes based on what they learned, then that will be considered a positive outcome. Looking ahead at the schedule, after Milwaukee leaves the arena 10 minutes from now, we will prep the arena for the University of Utah, and then our final team, I don't know how we're doing on time, our final team, if the pit boss decides that we have time for a final team, our final team today will be Colorado School of Mines. Nine minutes left in this run. Run 1 of 2 for Milwaukee School of Engineering. Milwaukee's second run, looking ahead at the schedule, is going to be basically the last run of tomorrow, assuming we stay on the current schedule, which means that Milwaukee will have essentially more than 24 hours to work on what's going on with the robot right now. Now, if they dig right now, I hope that digger on the right doesn't hit the motor that's kind of sticking out. Just missed it. So it looks like the students are taking advantage of the time they have in the bin, decided to stop driving around, and let's just get some experience digging. Oh, it just hit that motor. Hopefully it didn't do damage. So this is the dumping direction. I should point out, and you can see it in the corner of the screen, that this team did fill up their 4 bucket drums in their first run, and they did dump all 4 of their bucket drums into the scoring zone. So their score is not going to be 0, even though they've had all these problems with mostly with the steering of the robot, it appears. Impressive that these wheels, as buried as they are in the Regulus simulant, are still able to drive. I just noticed that the strings or cables that are holding the arms and raising them and lowering them are actually a block and tackle system, which is a pulley system, multiple pulley system that can reduce the force required. You're basically trading force for length. You can pull that string a long ways and it will pull up the arm a little ways, and you're trading length of pull for a large amount of force. Cool design choice. Did not give them any trouble as far as we can tell. The thing that really hurt this robot in this run appeared to be the steering system on the 4 corners of the robot appeared to get out of sync, and the steering wheels just got out of sync with each other, and the students apparently were unable to fix that in real time, sadly. I guess this is another trade-off that I didn't think about, is having your software so robust that you can just change anything under the sun at runtime. That's probably not trivial to implement, and so probably not a lot of teams are going to be able to do that. But maybe certain parameters are worth exposing to the user at runtime and making sure that the user can change them at runtime. so many trade-offs that these student teams have to decide what's worth their time and energy and what's not. This is actually the camera that the students are using in the control room, and they're controlling this camera view. Looks like they activated all their motors simultaneously during their last few minutes. It's almost like they're trying to see how deeply they can bury their robot in the last few minutes of their run. The students are in good spirits. Their smiles. Obviously, they're wishing that they had a better run, but their spirits are up. So the students are actually zooming in this camera to look at certain things. I'm actually surprised that this, as much as they've spun their wheels here, that the robot didn't dig itself deeper, but I guess every one of those 6 motors, those wheel motors, is just sitting on the ground and just not going to go any deeper. So the wheels are kind of floating in some fluffy stuff right now, I suspect. Just being held up by the motors themselves that are sticking out from the wheels. Those black tubes sticking out from each wheel or each motor. As time runs out, the Milwaukee School of Engineering robot waves at us. Let's give him a hand. That was a really good effort by the Milwaukee School of Engineering school team. Next up, we're going to have University of Utah, and after that, Colorado School of Mines. So don't go anywhere. You're watching NASA's Lunabotics 2025 Finals event, streaming live from NASA's Kennedy Space Center Visitor Complex. Don't go anywhere. You don't want to miss Utah and Colorado School of Mines coming up next. All right, you are watching NASA's Lunabotics finals for 2025, the 2024-2025 school year. And on the screen, you can see the University of Utah team, both in the arena and in our Mission Control Center. During their 10-minute setup time, they have a couple minutes left in their setup time. I don't see any panicking going on. I feel like the team is probably ready to start their first of 2 competition runs. University of Utah is going to run, and then Colorado School of Mines is going to be our last run for the day. But we still won't have gotten through our 10 teams' first run, so tomorrow we'll pick up the last 3 of our 10 teams. Tomorrow we'll do Purdue, University of Illinois Chicago, and University of Akron in the morning, and then College of DuPage in the afternoon. That will get us through the first run of all 10 of our competing teams, which is why we run this competition for 3 days. It takes us a day and a half to get through a run, and we want to give each team 2 runs. I see some students' hands on the robot, doing some last-minute adjustments. You can see in this view, the students have placed black and white visual markers around the starting area for the robot to recognize and use to calculate its position in 3D space. Now it looks like the students are happy enough with the situation to exit the arena. Earlier I was zooming in the camera and just looking around this robot. It looks like it has cameras on all sides, left, right, front, back. And the cameras on the front appear to be depth cameras, 3 giving not just 2D visual color information, but appear to be depth cameras that can give 3D information in addition to 2D information. I notice there are 2 cameras on the front of this robot. All right, we appear to be waiting for all of the checklist items for the arena and the... Okay, see the timer has reset and we are about to start the 30-minute run right now. And the robot is moving. I do see the student in the control center controlling the robot using a joystick. So they may try autonomy later on in their run, but they do not appear to be running autonomously right now during the beginning of their run. All right, the robot from University of Utah has exited the starting zone and is now heading toward the obstacle area of our course. and the student does not appear to be using cameras provided by Lunabotics. They are staring intently into their laptop, which has cameras live streaming directly from the robot into the student's computer. In the room just a minute ago, we had an announcement about a launch tonight, which is great that these students who have traveled from all over the country to be here this week are able to witness a rocket launch tonight. Could make for a little bit of a late night for some of these students, though, so hopefully staying up late for the rocket launch doesn't impact their performance tomorrow in the competition. All right, this Utah robot looked like it wanted to maybe pick up that rock and either push it out of the way or maybe take it into the scoring zone. Again, students are controlling this robot with a joystick. All right, now they're ignoring the rock. Probably a good idea. You'll notice the wheels on this robot are multicolored. Those colored sections look to be 3D printed, and oftentimes 3D printed parts end up being different colors based on the filament material you happen to have handy. You can also do that on purpose, especially for rotating parts, to actually see the motion and be able to count revolutions. So totally possible that the seemingly random colors were actually completely done on purpose. The University of Utah robot is a four-wheel drive robot, skid steer, so the wheels don't actually steer like the front wheels of your car. They all are going to be pointed straight like the rear wheels of your car. And robots whose wheels don't steer will just rotate in the opposite direction from side to side in order to change the robot's direction. Their excavation implement is a front loader bucket. And their robot appears to be powerful enough to push that front loader bucket pretty deep into this relatively tough material. Even though it's all particulate material, it's all very small particles. Once you get down a few inches, it's pretty tough because those particles are jagged and they lock together, just like lunar soil. That's why we use it. We're really early in this 30-minute run, only 5 minutes in, and this University of Utah robot has already made quite a dent in the middle of the excavation area. Look and see how much they loaded up that bucket right there. It's a good heavy load. And I imagine that the student drivers have started out a little conservatively, and I imagine that they'll get a little more aggressive as time winds down. The tread on these 3D printed wheels I find interesting. It's facing in different directions between the front wheel and the rear wheel. I suspect that that is a conscious decision. Oh boy, there's a rock there that the motor appears to have kind of high centered on for a second. Right there, the motor just hit the rock. And there the rear motor just hit the rock. There they go. That's one way to get your motor up out of the way. Again, this is University of Utah, also known as the U. University of Utah is in Salt Lake City. This robot's plenty powerful, doesn't have any trouble driving over rocks, driving through craters. Occasionally, one of the wheels decides not to drive while the others are. That's a little concerning. Because typically in a four-wheel drive robot, you really do need all four wheels to be driving and applying pressure. Otherwise, you could slip. And if you slip in this unique Regulus simulant, you could bury yourself if the conditions are just wrong. This robot is making quite a dent in our excavation zone, though. This side view gives you a little better feel for the dent that they've created on the right side of the screen and the berm or hill that they're creating in the scoring zone on the left side of the screen. It's a pretty good load right there. Front loaders like this, you have a decision on the angle that you set your floor of your bucket. I may not be using the right terminology. I'm just a software guy. And you also get to decide how hard you push down on the arm to push that bucket down into the earth or the moon, I guess. So, not a trivial operation to do this well. Of course, these teams have been practicing this operation to the best of their abilities. Not all teams have a really good Luna Regulus simulant, though. There you can see the team, especially the driver holding the joystick there. He has a laptop in front of him, in addition to the monitor, which is showing our facility-provided overhead camera. So of the two cameras that we provide, this team has decided to use the overhead camera. And they've chosen not to use the pan tilt zoom camera that is more of a side view or a diagonal view. He's pushing that rock again. Maybe he's trying to pick up that rock. I'll be impressed if this robot can pick up that rock and carry it over to the scoring zone. It can definitely roll it one side at a time. It might take a while, but it definitely has the power to do it. It's pretty impressive. Not only was it pushing regular simulant into the bucket, it was also pushing that rock. Now, some of the wheels are not turning, which is a possible concern for this team. It's possible that they're just temporarily hitting a limit, these motors, and as soon as they get past it, they start working again. Oh, that is a lot of regolith right there. That's a load, folks. That is heavy stuff, too. It's heavier than it looks. It is a lot heavier than sand. It is so dense. The driver is picking different spots, which is probably the smart thing to do. It'd be better in the long run to create a wide, shallow hole in the digging area than a deeper hole that's maybe not as wide that could actually cause your mobility system problems later. So maybe utilizing this entire zone for an aggressive robot like this, probably a good choice. You can see the driver was just fine-tuning the angle of the bucket just then before driving forward. Don't want to go too sharp of an angle and try and overdo it. No, I just during that view, when the two front cameras were facing us, I just figured out why there's two front cameras. One of them is facing forward to look at the surface in front of the robot, and one of them's actually facing almost straight down, kind of pointing downish toward the bucket to maybe see how much material's in the bucket. You can see how deep this robot in just 15 minutes has dug in the excavation zone from the side view. You can also get a sense of the piles that have been dropped in the scoring zone from this side view. It's a lot harder to see from the overhead view. It's a lot of material, and look how much time's left. 15 whole minutes for this team, this University of Utah team. All right, this team has decided to switch lanes, so to speak, in the digging area. Go back to the center of the digging area for a while. That's a good bite. That's a good bite of material right there. That's a lot. That rock is, they're just straddling it right now. It's right on the edge of being in their way. If they were to push on it one more time, they might be able to just push that rock into the scoring zone, I think. This student has some good driving skills and some good front loader skills. The large diameter wheels on this robot give it a lot of ground clearance. So this robot is barely concerned, maybe just very minimally concerned about that rock right there. The student who's driving is doing a great job getting some encouraging advice from teammates. "12 minutes left in this first run for University of Utah, the U. That's exactly why we used flexible poles to mark the position of our scoring zone, because we knew that reasonable chances some of these robots would run into or run over those poles, so not a problem for us. And there's no penalty associated with that either. Unless, of course, the robot depended on that pole being perfectly upright. In that case, it would be a self-imposed penalty. Okay, there for a second, it seemed like some of the wheels were doing some weird stuff. This is an impressive first run for the University of Utah. This is a completely manually controlled run as far as we can see by watching the students in the control room. So it doesn't appear that they're going for any autonomy bonus points, but they may not need them if their performance is such that they just completely offset that. I suspect that since the robot has all these cameras all the way around it, especially the 3D depth cameras, that's a big load right there. Yeah, we got cheering in the room for that load. It is possible that this team is going to do autonomy in their second run, which is a little more risky, but could pay off if it works with bonus autonomy points. You can see from the side angle how deep their digging area is right now. If they continue to make it deeper and steeper and steeper on the far side, and also ends up being steeper and steeper on this near side, that could cause them some mobility issues, which is kind of what you're seeing right there. They have artificially created a very steep incline right where the robot is sitting, and that front wheel was not spinning just then. Uh-oh. They got a full bucket there. They're dumping a little bit out. I was worried about this the whole time they were digging in that same spot, and unless you kind of change up where you're digging each time, you're going to end up creating a steeper and steeper and steeper slope. 7.5 minutes remaining. They have offloaded a lot of material from their bucket to see if they can get up this slope. And they're offloading even more. Okay, they're just going to empty it. They might need to pick a completely different spot because they're digging in pretty deep. Look at those rear wheels. Look how deep. They're about halfway down. They're pulling themselves out of this hole right now. Oh, they're dragging the dirt backwards. They're trying to reduce that slope in front of them, it looks like. Still having trouble getting up that slope. But again, all the wheels were not turning. So if all the wheels were turning, maybe they could have gotten up there. One of the things that might be causing some of these wheels to stop turning is heat. This robot's been driving pretty hard for 25 minutes now. It's possible that heat is building up in these motors and causing them to get a higher current than normal. And if you hit a current limit, the motor just, for safety's sake, shuts off. Five minutes left for University of Utah's first run. I think they're going to be happy with the amount of material they have already in the scoring zone. A little bit of a shame that they appear to be in sort of a bad position right now. They dug so much in that one spot over and over that both the incoming slope and the outgoing slope appear to be too much for this robot. All right, we're looking at the students in the control room. They've put down the joystick and they're typing furiously on their computer's keyboard. Are they changing current settings? so that those wheels will stopping. Still typing. Joystick's in his lap. He's typing. What are they fixing? What are they troubleshooting? 3.5 minutes left. Such pressure for these poor students. How fast can you type in 3.5 minutes to save your robot? Oh, they're driving again. Two and a half minutes left. Another attempt to drive up that steep slope. Did not succeed. One more. They did get a little further. Oh, got a little further. They're inching their way closer and closer to driving out of that trench. Two minutes left. Ignore the countdown clock. We must have had a countdown clock snafu just there. The judges will know what time it is to stop this run for University of Utah. All right, I'm going to assume that was the end of their 30-minute run. Let's give the University of Utah a big round of applause for an amazing run. They should be very proud of the amount of material that they got into the scoring zone. All right, our last run of the day is going to be Colorado School of Mines coming up in a bit. So don't go anywhere. You do not want to miss Colorado School of Mines coming up next here at NASA's 2025 Lunabotics final event, broadcasting live from Kennedy Space Center Visitor Complex here in sunny Central Florida. Don't go anywhere. We will be back. We are about to watch the Colorado School of Mines team, our last team of the day, perform their first run in NASA's Lunabotics 2025 finals event. Students have been getting the robot ready. Students in the control room, the mission control room, have brought their computers and monitors, keyboards, mice, and joysticks into the mission control room, hooked up to our network, and are communicating with the robot, sending test commands to make sure that the robot is receiving commands. And in the next couple minutes, we will start a 30-minute timer, and this robot will be off and running for its first run of 2 competition runs this week at NASA Lunabotics 2025 finals event. We have the top 10 teams from the qualification rounds last week competing against each other this week at the Kennedy Space Center Visitor Complex in Florida. The team, this Colorado team, the students in the Mission Control Center are psyched. There's some energy in the control center. See, the students have grabbed their joystick, an indication that they may be driving this run manually, or at least the beginning of it. Colorado School of Mines, less than a minute left in their starting time, and about to start a 30-minute run. The robot is currently sitting in the starting position. Once the 30-minute timer starts, the students will drive the robot out of the starting position through the obstacle region. Try not to hit rocks and craters. Into the excavation zone, and then excavate material and bring it over to the construction zone to deposit as much material as they can deposit in 30 minutes. All right, the students in the arena that helped get the robot in the arena and power it on are now exiting the arena. And as soon as our judges are in their positions, ready to go, they will start the 30-minute timer for this team. This Colorado School of Mines team from Golden, Colorado. They call themselves Moon Pie, and this is their capstone design team. Students are actually controlling the camera that we were just looking at. Implying that they are going to keep that camera on during their run, even though that will give them a little bit of a point penalty. They think that the amount of material that they deliver is going to offset that point penalty for keeping that camera on. in as soon as the judges are ready and as soon as they make the call to our timing judge. The clock will start. All right, we're about to start this 30-minute run for Colorado School of Mines. And the clock has started. And they're out of the gate. They're out of the gate fast. Look, they've already made it. They've already made it through the obstacle zone, past the obstacle zone. Now they're driving through the excavation zone. I suspect they're going to turn the robot around so that its rear end is facing the deposit zone or the scoring zone. This is a 4-wheel drive skid steer robot that has a plunging bucket drum system. It's going to drive down beneath grade, beneath ground level, in order to pull up loose granular material. And then I believe they have a conveyor on board to hold the material and then convey it into the scoring zone. So they appear to be set up in a good position to start digging. It's possible that now they're going to start autonomy. Yep, I'm watching the students in the control room. They've actually put down their joystick, grabbed the mouse. It's possible that they are activating autonomy for this dig. Students do not appear to be panicking. They are typing on their keyboard. And something is happening. The bucket drums are rotating, and looks like we saw some material through that fall into their hopper through this clear plastic. Let's watch closer this time. The student has grabbed the joystick, by the way, just then. But But they have put the joystick down, so this appears to be an autonomous digging cycle. I think that might have been a shadow that I saw earlier. I don't think the bucket ladder system was down quite far enough to be digging just then, actually in either of those two cycles we witnessed. Students typing on the keyboard. Maybe reconfiguring the autonomy settings, possibly. And now we're hands off again. We're going deeper. You can see that bucket ladder going deep. Now it's hitting. It actually stalled. It maybe went too deep just then. Because there it came up a little bit. Probably not what they were trying for, and the robot actually came back, potentially hit the wall. I didn't have the camera on it to see how hard it hit. Hopefully that didn't cause any damage. Well, something fell off the robot, but it's still operating. Okay, going towards that rock is probably not what they want either. At least digging towards that rock is probably not what they wanted it to do. So it looks like they're manually repositioning the robot with the joystick, and then possibly activating an automated digging cycle, possibly. We'll see if the student puts the joystick down when the robot starts digging. All right, so digging has started. It's going down. It's driving forward, and it appears to be bound up. Actually, the student camera, which is this view right here, is a slightly better view, slightly better angle than our camera. So this is the camera the students are looking at. You can see the bucket ladder system going down. It's not spinning yet. Normally it spins and then goes down. And then, ooh. Yeah, the students are definitely stick driving the robot right now. I can see one student on the keyboard, one student on the joystick. They may have had some issues with their autonomy system and decided to just go ahead and drive manually. There's lots of joy from these students, so they're not. They're still having a good time. Even if the robot may not be doing exactly what they want it to right now. There's still plenty of time to recover. 22 and a half minutes left in this run for the Colorado School of Mines team. The three tracks you can see on the screen, the outside tracks are from the wheels, and then the middle track is from the digging system. So they've most definitely have dug, and it looks like we kind of missed it there because we were looking in a different spot, but when we weren't looking, it looks like they deposited, using their onboard conveyor belt, a little bit of the material that they had dug. So with 21 and a half minutes left, let's see how many how many cycles of that dig dump cycle they're able to perform. Seems like when this robot drives, at least right now in its current configuration, it drives super fast and the wheels just slip quite a bit. That may be causing control issues. Okay, right now this is a good depth. No, they as long as they can go slow, this is a good depth for them. If they go too fast, they bind up their digging system, which just happened just there. They're still digging though. You can see the digging trench that they just left behind from that. And there they're dumping. Seems like right now this robot has 2 speeds. Too fast and 0. I feel like that could be part of the issue. If they had finer control of the speed of this robot, they would be able to drive forward more slowly during the dig operation and not bind up their digging system. This is the camera the students are controlling, so you can see them zooming in and panning to watch the robot. This is probably the best angle of all of our cameras, because this is the only camera that can see the front of the robot, the digging side. Ooh, that went deep, but as soon as it went a couple inches deep, it bound up. "18 minutes remaining for Colorado School of Mines in their first of 2 scoring runs this week. Yeah, I was just thinking if they plunge their digger down slowly while not moving the robot, maybe they can get a full load without actually driving the robot forward. But they're gonna have to go down slowly or find a depth and drive forward slowly, I think, is the sequence that's going to work best. They're making progress. Here comes some more material into the scoring zone. Not sure how much they got on that run, because their digger didn't leave much of a visible path behind. You can kind of see through their robot there. Yeah, I don't think their digger was deep enough that time, sadly. This time you can actually see a path centered under the robot where the digger's actually making a little bit of a path there. So that time they definitely got some on board. Let's see how much comes out the back end. They had some on board that cycle, but not a whole lot. But I think they're learning each time what's going on with their robot. It's not going very deep. It's just scraping just a little bit. I think the students have realized if they go too deep, it binds up. "12 minutes remain in this run for Colorado School of Mines. They've been able to get a few small piles delivered into the scoring zone. But their autonomy attempt seemed to not work as well as they had hoped. And then after they took over manual control, some of the control systems appeared to maybe not be fine-tuned in a way that was most efficient. You can see they're driving the robot forward in in these quick jerky movements. I believe that's because their robot doesn't really have a slow speed right now in its current configuration. So they're trying to force the robot to drive slowly in high gear, kind of, sort of. This team also appeared to possibly have some sort of a issue with their digging system where it binds up rather quickly, rather easily, before getting very deep. Right now they're just barely skimming the surface, it appears. And if they go more than just a light skim of the surface, their digging system appears to bind up, which just happened right there. So they are, in the lower right hand of the screen, they are depositing material. They're not going to get a score of 0, but possibly a lower score than they had hoped. But let's hope that whatever issues are plaguing them, they'll be able to fix tomorrow. And hopefully we'll see a whole new robot for their second run that does exactly what the students want to at exactly the speeds and powers that they want them to be. That trench in front of the robot right now, centered, is the deepest one I've seen from this robot. That's where it had bound a minute ago, I believe. Eight and a half minutes remain in this run for Colorado School of Mines. Students in the control room obviously haven't given up on this robot. They're doing the best they can, given the current circumstances. They appear to be having positive attitudes also. Six and a half minutes left for Colorado School of Mines in their first attempt. looking ahead at the schedule, it looks like this team, Colorado School of Mines, will be having their second run on Thursday morning sometime, which gives him plenty of time to troubleshoot, debug, troubleshoot, correct, and fix whatever issues were plaguing them today in their first run. There we see the students in the control room making the best of a not ideal situation. This camera shows us a side view, which actually shows the piles that this team has been able to deposit into the scoring zone are not trivial. There's some material there. This is a great view of the conveyor belt offloading. So there's more material there than you would think. I think as this run has progressed, I think the students have gotten better and better with dealing with the situation that the robot is currently in. You can see the trench in the center of the robot, behind the robot, that this current run has created. So that's a good amount of regular simulant on board right there. Let's watch them offload it. You can see it through the clear plastic right there. Yeah, that's a good amount. They got to feel good about that. 3 minutes remain. Two minutes. Oh, one of their wheels is dragging now. That rear right wheel just then was not moving. I think it's dragging that one wheel. They got one minute left. I don't know if they're going to make it back to the scoring zone with that one wheel. That rear one is just dragging on the right side. Oh, they can make it. They can make it. 1 minute left. I think if they're creative with their driving, they'll be able to make it. Oh, robots. It seems like that one wheel motor has just given up, and now it's fighting them. 20 seconds. All right, that's a shame they didn't get that last one. Let's see how much was on board. They're going to go ahead and dump it here in front of the camera. All right, let's give Colorado School of Mines a big round of applause. Great job persevering, fighting through all the obstacles. So, what happened today was we ran 6 teams. We ran Michigan Tech, University of Virginia, University of Alabama, Milwaukee School of Engineering, University of Utah, and Colorado School of Mines. That is 6 of our 10 finalist teams. We'll run Purdue, University of Illinois Chicago, and University of Akron tomorrow morning, and then College of DuPage after lunch. And then we will start all over again. Oh, I'm on camera. Hi. We'll start all over again after lunch, and we'll run a few more teams before we run out of time tomorrow, and then the rest of the teams for their second run on Thursday. So tomorrow morning, just like today, we are going to be starting our live stream at 8 a.m. Eastern. And then our first team will run whenever they are ready. It might be around 9 a.m. Eastern. It might be before that. So just go ahead and plan on starting your watching for those that are not here in the building. We appreciate you all watching the live stream. We had hundreds of people watching today. Tell all your friends. It's going to be even more exciting tomorrow and even more exciting than that on Thursday. So tell all your friends about this live stream. We're on the Kennedy's YouTube channel. And I want to mention to all the all the students who, most of them have left the building already, but all the students who are competing tomorrow, and you know who you are, all of you who were in this building, don't stay up too late watching that launch tonight. Watch the launch and then go straight to bed, because you all have to be here tomorrow morning, okay? Don't party all night. Be responsible and come back here tomorrow morning and have a great day competing. Thank you for watching day 1 of the 3-day NASA Lunabotics 2025 finals event here from Kennedy Space Center, Florida. We will see you tomorrow morning right here, same bat time, same bat channel at 8 a.m. tomorrow morning. Bye. Thanks for watching.